Good morning, everyone. We will be starting the event at 9:30. I kindly request you to wait
stop sharing, and this we have to stop this.
Yes.
This one no need now.
Okay.
And here, where is this one? Here, not opening.
Double click.
This one,
Okay, okay. So
So
this
we have to
let
make
it be over here. We'll share the same thing again. We have to share the screen.
Okay, I will ask. 1 minute.
But are we doing it without any prior information? Like
No, I'm going to start.
Okay, okay.
After that only we have to.
Okay, okay, sure.
So director has come. Unmute.
Mute. Okay. Good morning, everybody. I welcome our director, Professor Bhaskar Ramamurthy, head of the department, Professor V. Vetribal, the secretary of NSMA 2021, Dr. Ramesh Kashilingam, all faculty members, invited speakers, and participants to the online National Symposium on Mathematics and Application to celebrate the birth anniversary of the gifted Indian mathematician Srinivasa Ramanujan. We start our program with a devotional song by Nivedita R.
கைத்தலம் நீரை கனி அப்பமோடவள் பொறி கப்பிய கரிமுகன் அடிப்பேணி கற்றிடும் அடியவர் புத்தியில் உரைப்பவர் கற்பகம் என வினை கடித்தேகும் மத்தமும் மதியமும் வைத்திடும் மரன் மகன் மற்பொரு திரள் புய மதயானை மத்தளவயிரனை உத்தமி புதல்வனை மட்டவிழ் மலர் கொடு பணிவேனே முத்தமிழடைவினை முற்படுகிரிதனில் முற்பட எழுதிய முதல்வோனே முப்புறம் எரி செய்த அச்சிவனூரை ரதம் அச்சது பொடி செய்த அதிதீரா அத்துயரது கொடு சுப்பிரமணி படும் அப்புன மதனிதை இவமாகி அக்குர மகளுடன் அச்சிறு முருகனை அக்கணம் மனமருள் பெருமாளே அத்துயரது கொடு சுப்பிரமணி பொடும் அப்புன மதனிடை இவமாகி அக்குர மகளுடன் அச்சிறு முருகனை அக்கண மனமருள் பெருமாளே கைத்தலம் நீரை கனி அப்பமோடவள் பொறி கப்பிய கரிமுகன் அடிப்பேணி கற்றிடும் அடியவர் புத்தியில் உரைப்பவர் அக்கணம் மனமருள் பெருமாளே.
Now I request Professor V. Retrieval to give welcome address.
Yeah, good morning to one and all. It is indeed my pleasure to welcome Professor Bhaskar Ramamurthy, Director IIT Madras, who is here to inaugurate the NSMA 2021 to commemorate 134th birth anniversary of the mathematical genius Srinivasa Ramanujan. The Department of Mathematics IIT Madras was established in the year 1959, the same year as that of the institute. The department offers MSc in Mathematics, MTech in Industrial Mathematics and Scientific Computing, and PhD programs. Now we are stepping into the 62nd year. We continue to adhere to high standards in teaching and research. This in fact attracts the best students for our MSc, MTech, and PhD programs. Now we have 40 faculty members, 102 PhD scholars, 82 MSc students, 44 MTech students, and a few postdoctoral students. The department is housed in the 5th and a part of the 6th floor of the new academic complex with an excellent ambience for teaching and research, and as the state-of-the-art facilities. Thanks to the vision and mission of our director also has sanctioned funds this year for 3 centers of excellence through the Institute of Eminence, Government of India grant. Well, the one is Center for Computational Mathematics and Data Science, Center for Quantum Analysis, Center for Algebraic Geometry. Our department is proud to have conducted this one-day symposium since the year 1988. It is the 34th consecutive year. Thanks to the illustrious lineage of professors like Professor P. Achudan, Professor S.N. Maji, and his contemporaries who initiated this event. And this year, Dr. Ramesh Kasalingam has put enormous effort to organize this event online. I'm absolutely sure that they're all going to benefit out of it. I extend a warm welcome to the speakers of the symposium, our ex-colleagues, current colleagues, students of our department, and the participants from various institutes across the country. We are looking forward to hosting you a memorable program. Thank you.
Thank you, sir. Now I request Dr. Ramesh Kashalingam to tell us about NSMA 2021.
Good morning to all. The Department of Mathematics IIT Madras welcomes Honorable Director, guest speaker, students, and all math enthusiasts to the National Symposium on Mathematics and Applications 2021. Our department has been organizing the symposium every year as a tribute to the memory of Srinivasa Ramanujan, one of the finest mathematicians the world has ever seen. The symposium brings you lectures from distinguished speakers on various areas of mathematics. Moreover, the NSMA also stands as the platform for current researchers to present their work to the fraternity of their area and thereby strengthening the network of mathematics learners in India. So I just briefly inform the schedule for this program. From 10 to 1 p.m. there are 3 invited talk, and 1 to 2 we have a lunch break, and 2 to 3 there will be another invited talk. So apart from that, 3 to 5 there is a paper presentation parallel session. It will be happen from different link which are already shared to all participants. And with the 5 to 5:30 we have a vote of thanks in the same meeting, the same link which we are now. So I hope all students and researchers, lecturer, faculty will enjoy this session, these symposiums, so that from one level to another level it will go from IIT by using IIT mathematics faculties. So with this brief introduction about NSMA, I hereby request Sain Das to please take over the stage for the next address. Thank you.
Thank you so much, sir. Thank you. So now I request our director, Professor Bhaskar Ramamurthy, to give the inaugural address.
Thank you. Can somebody confirm that I'm audible?
Yes, sir.
Yes, sir.
Okay. Thank you very much, and a very, very good morning to all those who are participating in this virtual Ramanujan Day Symposium. If there are people from abroad, good evening or whatever, early morning. But in any case, I think the fact that the mathematics department has been able to conduct this without a break for so many years, despite the pandemic, etc., is a commendable feat. Almost all departments at the institute conduct such symposia or research conclaves. They are very, very beneficial to the research scholars of the department. The scholars, of course, go to other conferences too, but this is a conference in some sense targeted at them. They get to hear very good talks from leading people in the field, as it is true for this symposium also. And they also get to hear some of their own peers who have done some good work. So it's a very good learning experience for them. And I would like to congratulate the department, mathematics department, for pursuing this without fail year after year. I myself have had the good fortune of inaugurating this for the last 11 years, I think. And I've seen how the enthusiasm has always been high. And when the symposium was held in person, most of the research scholars used to be present. And it's a one-day symposium, so it's not very exhausting for the students. I can see that this year's program also is very interesting. There are speakers from in different disciplines and also from different parts of the country. I suppose the virtual nature of the conference symposium makes it easier to for people from elsewhere to share their knowledge, because they don't have to travel here. It's also the year when one of our own has won the Ramanujan TST Ramanujan Prize from ISI, and a lady. So that makes us all very proud. And I really hope that in the next few years, a lot more good results, new breakthroughs come from India, from Indian mathematicians. We've been waiting for the hockey stick effect to happen. I hope it's happening now, because I think there's a lot of potential for India and Indians to contribute to knowledge in mathematics at the global level. We have to bring our base, our foundational base. It's not very different from what it is in, say, hockey or any sport today. The level of competition and the level of expertise at the highest levels is very, very high. And one has to, while one always needs a few stars, the real important thing is to have a very good foundation, broad and strong foundation across the country, so that you can keep bubbling up new talent. So it's very important for us to build this capability across our education, higher educational, from school onwards, actually, to instill in these children the fascination for mathematics, so that the ones who are, smitten by it, despite all the difficulties that they will face to really proceed, will take it up. But not very different from the way people who are very talented in music pursue it, or in some other, even in sport. And then the higher education system, the colleges, the universities, I think we have to really broaden and deepen the foundation so that the talent can bubble up. And then we have to give them the right atmosphere in the higher educations, in the universities, so that they can really come up with very important breakthroughs. So I wish, and on the other side, I think the applications of mathematics, the last, I would say easily last 6 to 7 decades has been very, very impressive. I myself belong to the discipline of electrical engineering, and the electrical engineering discipline has benefited enormously from developments in mathematics and its application. today, everything that we do, including this virtual conference, depends heavily on the leveraging of mathematics results that were that were discovered in the last century or two. If you take the whether it's the error correcting codes that are vital to this kind of communication systems that we deploy, so that we get the robust performance that we want, or whether it's the waveform representations, the decoding algorithms, the whole the whole, and if you take other disciplines, if you take even truck tire design today, it's heavily dependent on enormous progress in the field of partial differential equations and other things. So the applications of now and the latest of the statistics and mathematics in data science and analytics is really galloping. So I would say that both in terms of fundamental progress in mathematical knowledge as well as in the applications, these are very good times to actually build ourselves, build our capability, and I hope that this is not a one person effort or a one institution effort. I hope all the institutions get together and come up with some plan. In a way, I mean, we can take inspiration from what's happening in sports. I personally, I'm not a sportsman, but I'm impressed by the way India is going about it in the last few years at all this, because you see in every sports event now, we are coming to the right up to the top, and new people are coming up. People are coming from all over the country, from rural areas, from all states. So obviously something is changing. And I think a very similar thing hopefully is happening already in mathematics. And if it's not, all of you should get together and make it happen. And I hope that we will see very, very many more, good discoveries coming out of India, and good applications coming out of India, and India becoming, sort of a, in some ways, not, just like we hope that we'll become a reasonably good sporting country, we should become a good mathematician country. Thank you very much.
Thank you so much, sir, for such a inspiring speech. Now I request Dr. Ramesh Kashilingam to propose the vote of thanks.
Director Professor Bhaskar Ramamurthy, Head and Department of Mathematics Professor S. Vetrivel, Guest Speaker Professor Saju Krishnandu Gangobadia, Atul Tikstit, Dr. Samik Basu, distinguished member of the audience, faculty, colleagues, other invitees and participants of the National Symposium on Mathematics and its application. It's my pleasure to present the vote of thanks. On behalf of the department, I would like to thank Professor Bhaskar Ramamurthy for his inaugural address despite his busy schedule. I am thankful to all the speakers for accepting my request and agreeing to speak on this occasion. We all are looking forward to listening to this talk. I would also like to thank IIT Madras for the finance support, and a lot of hard work has been put in by the faculty members, research scholar, MSc students, postdoctorate student, and the supporting staff of the department. I extend my special thanks to Kannan Krishnamurthy, executive producer, senior consultant, for their streaming service. Also, I thank Perumal Raja and Srinivasan V for their technical support. I would like to individually thank them for all their efforts. Last but not the least, I would like to thank the participants for the symposium. Once again, thank you for all for making the symposium to happen. Thank you.
Thank you, sir. I now request all the participants and invitees to join us for the invited talks. We have 3 invited talks from 10 a.m. to 1 p.m. Then there will be lunch break from 1 to 2 p.m. And at 2 again, we join us with the same link for the another invited talk. There will be also live streaming of the program, and maybe you have all got the link in your respective emails. You can join there also. And the parallel paper presentation will be from 3 to 5. The respective links have already been sent to email. Please join us and make the event good. Thank you.
We will wait 10 minutes for the first invited talk, please.
Am I audible now?
Yes, yes.
Okay, okay. Now, shall I share the slides?
Yes, yes.
Yeah,
So, good morning to all. We will have now for our first invited talk by Professor Saju. I request Professor Nilesh to introduce the speaker and chair the session.
Ramesh, we are not able to share. So you have to give permission, I guess.
Yeah, I already even make him presenter as well. And now is it okay?
Yeah, I will try.
Is it okay? Oh, good.
So is it visible to you?
Yeah, Shaiju, it is visible.
Okay, thank you, thank you, thank you.
So we will start now. So good morning to all the participants. My great pleasure to introduce today's speaker, invited speaker, who is my colleague also, Professor A.J. Shaiju. So he has been serving IIT Madras since year 2009, and his main area of research is game theory. In particular, recently he is focusing on evolutionary game theory. So and then he has done his PhD from IISc Bangalore, and he has also done his postdoc from Australia for a period of 3 years. Okay. So now today he is going to talk to us, or he is going to share his expertise in the topic of game theory uh, through the talk entitled Games, Equilibria, Dynamics and Stability. Welcome, Shaiju. Stage is yours.
Yeah. Thanks, Nilesh. So my voice is audible to you?
Very much.
Yeah,
Yes.
thank you, thank you. Thanks once again to Nilesh for the kind introduction. And I would like to also thank head of the department, Professor Vetrivel, and the coordinator of this year's NSMA, Dr. Ramesh, for giving me an opportunity to make my presentation on this prestigious occasion where we are commemorating the birthday of Srinivasa Ramanujan. So I will get back to Ramanujan at the end of my talk again, but let me start my talk first. So today I will talk about game theory. So there are three important aspects of that I will cover today. One is equilibria, then stability, and also the dynamics. So all these three are very much connected each other. So I will try to illustrate through examples and certain theorems how they are connected each other. So here is the outline of my talk. So first I will present three examples, and motivating by these I will come to what is game theory in words. Then I'll come to the definition of a game, the formal definition of a game. Then after that, we will define what is called equilibrium in games. So it is named after the mathematician John Nash. So we will call Nash equilibria. Then again, through examples, we will see that we need to go to some randomized options. So-called mixed strategies. And there we will get existence of Nash equilibria. Then we need some methods to find the equilibria. So we will discuss fundamental theorem of Nash equilibria. And also we will discuss in particular the special class of games called zero-sum games. They enjoy further properties. After that, we will also see how we can calculate Nash equilibria using nonlinear programming. And at the end of the part 1 of my talk, I will talk about further refinements of Nash equilibria. What are the relevances of refining the concept of Nash equilibria? So that will end my first part. And in the second part, I will talk about population games and then replicator system. And then I will connect all the concepts we have discussed so far. Then I will conclude, and with the references I will finish. So that is the plan. So we have the first example, the famous prisoner's dilemma example. So here there are two prisoners. So just make the story little bit look good. Now prisoner is always a negative thing. So I would call them executives. Okay. So there are two executives. They have jointly committed some irregularities, financial irregularities. The police know that it is a very major thing, but police is having only very little evidence, so that they will get punishment of 1 year only. But police know they have done much bigger crime, but they don't have evidence. So what the police is doing, they will lock them up in separate cells. Then they present in front of them simultaneously this particular scenario or game, that each prisoner can choose either to confess or not to confess. So not to confess, we call it as defect. So there are two options each, C for confess, D for defect. And we have four scenarios here. If the first scenario, if both executives confess, the police is giving in the offer that both will be punished and they will get 6 years in jail. That's why I have written -6, -6, because by convention, game theory, we always maximize. So imprisonment, if they want to minimize, so I am giving the negative sign. Another scenario, if both executives decide to defect, then police don't have much evidence, they will get 1 year each in jail. On the other hand, if one decides to confess, other not confess, then the not confessing executive will get 10 years in jail and the confessing executive will be set free. So that is why this self-explanatory, the payoff structure is self-explanatory. So this payoff matrix has 4 entries. Each entry has 2 components. So the first component will be the payoff to the raw player, and the second component will be the payoff to the colon payer. So now, in any scenario of this kind where interaction and decision, interactive decisions are coming, there are 3 constituent elements here. One is the players involved, and second, the options they have, the strategies they have, and third, the payoffs they get. Here it is the imprisonment. So let us go to next example. So in the next example, we have the game of chicken. So here, of course, chicken means not the chicken we have. It is the local meaning, say in US, chicken means covered. Okay. So this is a game played by teenagers, maybe almost 70 years back in US. So 2 teenagers are there. So teenager 1 and teenager 2, they in the same road in the opposite direction, in a tiny road, they drive the car towards each other in high speed. So each of the teenagers have 2 options. I call it as S1. So I am introducing some notations also here. S1, which is our first option, they can go straight. And S2, the second option for teenager 1, is they can swerve. That means they can move, take a turn and escape. So these are the 2 options, straight or swerve. Okay. So similarly, the second teenager also has the same options, but we call it as T1 and T2. Okay. So in the first scenario, if both teenagers go straight, there is a collision, they both are badly injured. So that's why I have written minus, because they are losing. So -2, -2. Now, if both are swerving, both are escaping, so they are not getting anything. So 0, 0, nothing to everyone. Then, on the other hand, if one decides to go straight, other escaping, the straight going guy will be a winner in front of the peers. So he gets the pride that he is a big man. So he is getting 1. The other guy loses his face, he gets -1. So this is the game of chicken. Here also there are 3 constituent elements in this competition. Players, teenagers 1 and 2, their strategies, S1 and S2 for player 1 and T1 and T2 for player 2, and the payoffs, respective payoffs, which is given in the biometrics. So in a biometrics, each entry is an ordered pair. In the ordered pair, the first component is the payoff going to the first player, and the second component goes to the second player. So that is the convention. Now let's go to the next example, the third example. So this is the so-called hawk-dove game. So this is very famous in the biological literature or ecology. So here there are particular species of animals. If you want to fix ideas, you can think that they are birds of particular species. So they can either behave like a hawk, always go for fight, or they can behave like a dove. It's a conciliatory behavior. So if 2 hawks come together, they keep fighting and one will get badly injured and he loses, the other guy wins. The winning guy gets the reward V because they are fighting for some resource of value V. But the guy who gets injured badly, that injury cost is C. Okay. So that is why on average the hawk population, one is getting V and another is getting -C. So that is why V minus C by T, C by 2. V minus C by 2, V minus C by 2 on average goes to the hawk population. Then you look at the other scenario. If both are dove conciliatory behaviors, then what will happen is that both birds, they keep displaying their strength. They never go for fight. But eventually one will get bored and retreats. He will not get anything. He will get 0. So other guy who persists will win. He will get V. So on a entirely the dove population, you see V by 2, V by 2. So V plus 0 by 2. So on average, they are getting V by 2, V by 2. On the other hand, if a hawk and a dove comes, the hawk, of course, go for fight, dove flee. So the hawk will get V and dove will get 0. So this is another example of interactive decision-making scenario. So these are the 3 examples. So what is game theory? So in words, this I am taking this quote from this famous book by 3 mathematicians, Maslach, Solan and Solan and Samir. This is Cambridge University Press. This is a very comprehensive book in game theory. It is about 1000 pages. So this has all the elementary materials and almost all the higher level stuff also. So it's very, very, very well written book also. So they say that the game theory, we can think it of as analysis of situations where interactive decision making is involved. So it is analysis of conflict. So in a scenario of this conflict, it will predict what the players would choose. Also, if you are an individual player, it will give methods for how you to choose your actions optimally. So this is what game theory is. Now let us formally define it now. So in this talk, we restrict ourselves to 2-player games. The competitions involve only 2 players. This is just for convenience, the ease of presentation. So for us, the game is a triple. The first constant element in the triple is the players P1 and P2. The second constant elements is S and T. So S is the set of all options or actions for player 1, and capital T is the set of all options or actions for player 2. And the final and the most important constituent is the payoffs. So that is pi 1 and pi 2. They are the payoff functions to individual players. So here, note that the action set or the strategy set for player 1 is the set S. That is a finite set S1, S2, Sn. Similarly, the strategy set for player 2 is capital T, T1, T2, etc., Tm. So this matrix, if you see, it is a n by m matrix, the corresponding payoff matrix. Aij is equal to pi1 of Sitj, Bij is pi2 of Sitj, when these are the payoffs respectively to players 1 and 2 when they respectively adopt the strategies Si and Tj. So such a game can be represented by a bimatrix, n by m bimatrix. Each entry of the matrix is an ordered pair, Aij, Bij, and Aij is in terms of pi1 and Bij is in terms of pi2. So each player, as I have mentioned in these examples, each player, for example, if you are player 1, you would try to choose an option Si so that you want to maximize what you get, pi1 of Sitj. While trying to do so, Tj is not in his control. So it is in the control of the other guy. Similarly, the player 2 wants to choose a Tj so as to maximize pi2 of Sitj, which is Bij. So when he tries to do that, Si is not in his control. So this is a interactive decision making scenario wherein each players want to choose optimally and maximize respectively what they get. Next, let's go back to the prisoner's dilemma example. In that, please recall that each players have two options each. S1, S2 is C and D, confess or not confess. Similarly, T1 and T2 also confess and not confess. So in the first scenario, we have C comma C. That is S1 comma T1. Pi1 of S1 T1 is minus 6, or A11, that is minus 6. B11 is minus 6. Note also that in this scenario, if player 2 unilaterally deviates from his option, what is his option here? Originally, he was planning to take C, confess, but he unilaterally deviates to D. So now the game will become C comma D. Then what is happening to player 2? The executive 2, instead of getting 6 years in jail, he is getting 10 years in jail. So by deviating unilaterally from his strategy, he is losing. Similarly for player 1. So you start with a pair C comma C. There each of them are getting 6 years. If P1 also deviates, he also is going to get, instead of 6 years, he is going to get 10 years in jail. So such a pair from which any player unilaterally deviates is a loser. He will not get anything. Such a pair will be called Nash equilibrium. Now, if you see in the same game, you look at the pair D comma D, that is S2 comma T2. There, each of them are getting 1 year in jail. But suppose player 1 is deviating from that. He is choosing C. So game will become C comma D. So player 1 is getting what? He is benefiting. Instead of getting 1 year in jail, he is going to get no jail imprisonment, 0. So from the pair D comma D, players can deviate unilaterally and benefit. So that pair is not an equilibrium, right? If there is a benefit, people will switch. So it is not an equilibrium. But on the other hand, we have seen C comma C is an equilibrium. Both of them don't gain by unilaterally changing. So that's why the C comma C is an equilibrium and D comma D is not an equilibrium. Similarly, you can also verify the other options S1 T2 and S2 T1. They are not equilibriums. The only equilibrium in this case will be the executives are in a way forced to cooperate with the police, and they get 6 years in jail. Okay. So this motivates our formal definition of the Nash equilibrium. So let's go back to the formal notation. We have a game, triple, P1, P2, S comma T, their strategy sets, and the payoffs Pi1 and Pi2. A strategy pair or a strategy profile, S star comma T star. So a pair is also called a profile in game theory. Pair or a tuple is also called a profile. So we use this interchangeably, pair or tuple. So a strategy profile, a star comma T star, is called a Nash equilibrium. If, of course, in words I have explained what it is. Let me explain that in notations. We have two sets of inequality. The first set of inequality says that for every S which is not equal to S star, that means the player 1 is deviating from S star, then what he gets, Pi1 of S T star is less than or equal to Pi1 of S star T star. So there is no incentive for player 1 to deviate. Similarly, for player 2, Pi2 of S star T star is greater than or equal to Pi2 of S star T for every T not equal to T star. Here, this is called Nash equilibrium. If here the inequalities in both this set of inequalities, these inequalities are strict. Whenever S not equal to S star and T not equal to T star, we may call it as a strict Nash equilibrium. If they are not strict, just greater than or equal to, then we can call just Nash equilibrium. So as I explained the detail in the previous slide, in the prisoner's dilemma game, we have already seen that the pair C comma C is a Nash equilibrium because anyone deviates unilaterally is going to lose. It is in fact a strict Nash equilibrium. So let us also look at the next other examples. So we have come back to the chicken example where the options were go straight or swerve. Here you look at the option, for example, S1 T1, straight. You can see that anyone who deviates from straight and other teenager stick to it. Say, suppose teenager 2 changes from straight to serve. What he gets? From instead of getting -2, he is getting -1. So he is benefiting from deviating. So this pair straight or S1 T1 is not a Nash equilibrium. Now you look at S2 T2, which is the pair, the second, that serve swerve. So in that both are getting 0. So if one of them deviating, so the deviating again will benefit. So that is also not a Nash equilibrium. Now you come to the pair S1 T2. That is the pair straight comma swerve. So you can see very easily that in this pair straight comma swerve, any player who deviates does not benefit. So the straight comma swerve is a Nash equilibrium. Similarly, analogously, we can also see that ulta, that serve comma straight, that is also Nash equilibrium. So this game we can see immediately two Nash equilibria. One is S1 T2, another is S2 T1. Now let's go to the next game. Hawked out day game. Okay, to fix ideas, let me take the cost of injury here to be 6 and the value of the resource V to be 2. So here I are assuming that the cost of injury is much higher than the value of the resource. Okay. So in this game, then the payoff matrix will become -2. Then we have dow will get 1. Otherwise, we are getting 2-0 or 0-2. So in a sense, structurally, this game is also same as the previous game of chicken. Because the hawk is not an equilibrium, dow is not an equilibrium. The S1 T2, that means hawk dow is an equilibrium and dow hawk is also an equilibrium. So very easy to observe that. So we have 3 examples, and we have seen in all of this, in each of these 3 examples, we have seen either 1 or two equilibria. Now we'll have one more example, which is the so-called rock, paper, scissor game. So this is a toy game which is played by children. We are familiar. Some of you are definitely familiar with it. So there are two players again. So they have three options each. Rock, that means you show your closed fist, rock. Then paper means open hand. Then we have scissor, closed fist with your index finger and your forefinger, right? The middle finger, index finger out. So what happens is that if you same strategies, rock and rock means a draw, scissor and scissor means a draw, paper and paper means a draw. But if rock and paper comes, the paper wins. And if rock and scissor comes, rock wins. And if what is the other possibility? If scissor and paper comes, then scissor wins. So what happens is this is a cyclic behavior. So rock is beaten by paper, and paper is beaten by scissor, and scissor is beaten by rock. So these have a lot of applications in biology where we have, say, three types of bacteria, and each cyclically can kill each other like that. So coming back to rock, paper, scissor game, here the payoffs are 0-0. Diagonally we have 0-0, 0-0, 0-0 because there is a draw, tie. Then all other places we have either 1, -1 or -1, because one. So for example, if rock plays paper, paper wins. So in our 1-2 entry, first row, second column, the payoff will become -1-1 because rock is losing, paper is winning, like that. So this is an example of also a zero-sum game where whatever player 1 gets is the minus of what player 2 gets. Their payoffs add up to 0. So what is more important is that here there is no Nash equilibria. In whatever actions we are considering, rock, paper, scissor, no Nash equilibria. You can verify that in any pair you take, whether it is a rock or rock paper or any pair you take, there will be at least one player who can deviate and benefit. So this game has no Nash equilibria. But if as a child you have ever played this game, you know an intuitive equilibrium of this game, motivated by the fact that, see, if you always, suppose you keep playing it iteratively, this game with your friend, suppose you are always playing rock, then other player will always play paper and he wins. And suppose you are always playing paper, then other guy can always play scissor and he wins. So you should not stick to one particular option. You should play a randomized strategy here. Okay? So you should keep randomizing your strategy. Then other player cannot predict what you are going to do. Okay, so that is the motivation of mixed strategy, and we are going to define it in the next slide. So mixed strategy is a compulsion. If you want to get the existence of Nash equilibrium, you need to go in general to mixed strategy framework. So if you have a game which is a triple, we have players and their strategy sets S, T, and their payoffs pi 1 and pi 2. Then you look at the strategies S1, S2, Sn for player 1, a n tuple x equal to x1, x2, xn. This is called a mixed strategy for player 1 if each of these components x1, x2, xn all are non-negative and they add up to 1. So interpretation is that this x1 is the probability that you choose the first pure strategy S1, and x2 is the probability that you choose the second pure strategy S2, and so on. Similarly, we have an m tuple t equal to t1, t2, tm for player 2, and tj is the probability that second player is going to choose is jth pure strategy, right, which is tj. So yj is the probability that he is going to choose his pure strategy tj. So x1, x2, xn is a mixed strategy for player 1. Y, y1, y2, ym is a mixed strategy for player 2. Now, when player 1 is choosing x and player 2 is choosing y, the expected or average payoff going to player 1 is the summation. So expectation is the summation overall INJ xi multiplied by yj, then pi 1 of SITJ. Why? Because the probability that simultaneously player 1 is choosing SI and player 2 is choosing TJ is the product xi times yj, because the players are choosing their actions independently. That is the basic assumption. So then when they do that, they get pi 1 of SITJ and pi 2 of SITJ. So the expected payoff, this summation, we can also write concisely as a matrix form. The vector, the raw vector x multiplied by the n by m matrix A multiplied by the column vector y transpose, x a y transpose. So that is the expected payoff going to player 1. And similarly, the expected payoff going to player 1, player 2 is x b y transpose. So note also that when we talk about randomized or mixed strategies, you take the n tuple or m tuple 1 0 0 0 0 0. That means that you are choosing the first pure strategy with the probability 1. So it is identified with the first pure strategy S1. Similarly, 0 1 0 0 0, that is identified with the second pure strategy S2 or T2 respectively for player 1 and player 2. So that is the thing. So next, you look at the collection or the set of all mixed strategies for players. It is actually a simplex set of all x such that their components are non-negative and they add up to 1. So if you look at in Rn, geometrically, the delta of S is the set of all mixed strategy for player 1. Geometrically is the, you look at the plane x1 plus x2 plus xn equal to 1, that is a plane of dimension n minus 1. And that part of the plane which is contained in the first orthant, x1 greater than equal to 0, x2 greater than equal to 0, and so on. So that is actually a simplex, we say. So delta of S mixed strategy space is actually simplex for player 1. Delta of T similarly is a simplex, mixed strategy simplex for player 2. Now we can similarly define the Nash equilibrium in mixed strategies, the same way as we have done for pure strategies. The definition is similar. We say that a mixed strategy profile x star y star is a Nash equilibrium if pi 1 of x star y star is greater than or equal to pi 1 of x y star for every x. If player 1 is deviating from x star to x, he doesn't gain much. Similarly for player 2. So here note that the first inequality, pi 1 of x star y star, which is greater than or equal to pi 1 of x y star. Here y star is fixed, other guy is not changing. Player 1 is shifting. So x star is a maximizer. That's what it says. X star is the best response against y star. If the other player is sticking to y star, as a player 1, the best possibility for me is x star. Of course, x star need not be unique. It's one maximizer we are taking. Similarly, if x star as a player 1, he fixes x star, the other person, the y star is the best response. So in a sense, a pair or a profile x star y star is a Nash equilibrium. Equivalently means that x star is the best response against y star. We denote it by saying that x star belongs to B of y star and y star belongs to B of x star. They are best against each other. Right? It is just like husband and wife. Right? So whenever there is a conflict scenario, right, at least one of the persons should just go away and you just postpone the fight. They are best against each other. Anyone who is married would know that. Right? So they are in equilibrium. If they keep fighting, then they are not in equilibrium. Okay. So that is the mixed strategy, Nash equilibrium. And we go to next slide. So why we are going to mixed strategy equilibrium or mixed strategies is that we are actually convexifying the set of actions we have. The pure strategies, which we can view it as the vertices of the mixed strategy simplex. You are just convexifying that. So once you convexify, you get all the convex combinations of that you get as members of the simplex. Okay. So because of that, we get the existence theorem of Nash equilibrium. So this was established in a little more general form by John Nash in 1950. The theorem is the following. You consider any game. This game has at least one mixed strategy Nash equilibrium X star Y star. So the proof is, I can explain it very easily because I'm using a very powerful theorem inside that. So idea is very simple. You define a map from the Cartesian product of the mixed strategy simply as delta of S Cartesian product with delta of T to itself. The map is F, but this is not a point-to-point map. This is a set-valued map. For each x comma y, I define f of xy to be the set, which is a Cartesian product of b of y cross b of x. So b of y is the best responses, the collection of all best responses against y, Cartesian product with the collection of all best responses against x. Because of the way we have defined the mixed strategy framework, it has linearity in each variable, and therefore we have continuity, and the simplexes are compact subsets of the Euclidean spaces. So we have all the linearity, continuity, compactness arguments with us. We can show that for each pair xy, this f of xy is a non-empty closed convex subset of the compact space we are in. So because of that, and also we can show that this map f of xy is a upper hemi-continuous. So it is a kind of closedness of the graph of this function. So all the conditions required for the application of the so-called Kakutani fixed point theorem is valid here. One can verify, and therefore by the fixed point theorem, it follows that this set valid map has a fixed point, x star, y star, say. That what is the meaning of that is a fixed point? That means x star, y star, the pair, it belongs to f of x star, y star. That is equivalent to saying that x star is best against y star and y star is best against x star, and hence it is an equilibrium. So if you apply the fixed point theorem, it is easy to show the existence. So that is the existence of a Nash equilibrium. So the existence is not enough, as we all know. We also need to compute them or find them in examples. For that, what we will have is the so-called fundamental theorem of Nash equilibrium. So to explain what it is, just one notion I will introduce here. That notion is like one pure strategy is active in a mixed strategy. What is the meaning of that? The meaning of that, you take any mixed strategy, x equal to x1, x2, xn, some of them may be zero, some of them is strictly positive. So those components which are strictly positive, the corresponding pure strategies, we say they are active in the mixed strategy. For example, you look at the rock, paper, scissors game, it is a three option, n equal to 3. You look at the x equal to 0.1, 0.9 and 0. You can say that a rock, the first action, and second action, second pure strategy is paper. The rock and paper are active here. But because the third probability is 0, the scissors, that option is not active here. So that is the notion of active. Okay. So with this, I can present the fundamental theorem of Nash equilibrium, which says that a pair x star y star is Nash equilibrium if and only if the following two conditions are satisfied. The first condition says that you look at x star y star and you fix y star for player 2. As a player 1, you look at two pure strategies S and S prime, which are active in x star, then they should earn the same against y star. Because if they don't earn the same, one will be strictly less than the other, then whatever is strictly less, there is no point in choosing that in the equilibrium. So that's why if x star y star is an equilibrium, we should have all the pure strategies which are active in x star should earn the same against y star. Similarly for the other player, right? Any t and t prime which are active in y star should earn the same against y star. So that is the first condition. Second condition is that if S is active in x star and S prime is not active in x star, then what is active? S, that should earn greater than or equal to the other one. Similarly for player 2. So these two conditions are equivalent to x star y star being a Nash equilibrium. if you look very carefully, this we can see that this pi 1 and all equivalently they are matrices. So we can see that for a two-player game, this all linear inequalities will come. In general, for n-player game, these all inequalities which is given by these two equivalent conditions 1 and 2, they are all polynomials of degree n minus 1. So basically what is happening, because of the fundamental theorem for an n-player game, the finding Nash equilibrium gets reducing to verifying certain polynomial inequalities. So that is the advantage of fundamental theorem. Okay. So now let us go to example. So Hawk-Dove game, you go back there. We have the payoff functions. V minus C by 2, V minus C by 2. And we have V0. Then we have 0 V, then V by 2, V by 2. So if you look at only metrics for one player, it is just V minus C by 2, V, then 0, then V by 2. Here we have already observed that there are two Nash equilibria in pure strategies, which are Hawk, Dove and Dove, Hawk. Now what we can see is that there is also one more equilibrium here which is in mixed strategies, which is physically very relevant also. We will come to that later. So use fundamental theorem we will use to find that. So let us assume that there is a Nash equilibrium in the mixed strategies. Call it x star equal to x1 star, x2 star, and y star equal to y1 star, y2 star. So assume that all the pure strategies are active in x star and y star. Then what they are saying is that if you are looking at from players 1's point of view, against y star, both pure strategies, Hawk and Dove, should earn the same. So that will give you the inequality, the equalities, the ends and the same, so it should be equality. That is pi 1 of S1 y star is equal to pi 1 of S2 y star. Now pi 1, pi 2 values you substitute, what you are getting, minus 2 y1 star plus 2 y2 star equal to y2 star. That's what you are getting. Similarly, we have an equality, another equation, right, for player 1. So one in x star and one in y star. And also note the fact that they are mixed strategies. So all these variables x1, xi star, yi star, they are all non-negative and they add up to 1. So use all the information. You are getting the fact that x1 star is 1 by 3 and x2 star is 2 by 3. Of course, we are taking v equal to 2 and c equal to 6 here to make our calculations simpler. Okay, so not only that this has pure equilibria, this has also a mixed equilibria. It's in the case it is 1 by 3, 2 by 3. That means that with probability 1 by 3, I should adopt Hawk behavior, and with probability 2 by 3, I should adapt Dove behavior, and that is optimal for both. That's also another equilibria. Now let's see one more example. Go back to rock, scissors, paper game. So here we had already observed that this game did not have an equilibrium. Okay, this game did not have an equilibrium in pure strategies, but we can show that this has an equilibrium in mixed strategies. So because of lack of time, I am not going to details here. You just use the fundamental theorem. Assume that x1 star, x2 star, x3 star, and y1 star, y2 star, y3 star, they are equilibria. Then you use the equality coming from the condition 1 of the fundamental theorem. You get equations as shown here. You can solve them and verify that this x star equal to 1 by 3, 1 by 3, 1 by 3, and y star is also equal to 1 by 3, 1 by 3, 1 by 3 is an equilibrium, which is an induction also. You should play a rock and scissor and paper all with equal chance to reach an equilibrium. So that is about the Nash equilibrium and the existence of Nash equilibrium. So what is the next slide about? Yeah. So now we come to a special class of games called a zero-sum game. So I have to go through this section quickly because we are approaching time. So in the rock, scissors, paper game we have seen earlier, it is example of a zero-sum game. So we have payoffs like 0, 0, minus 1, 1. They all add up to 0. So those games where pi 1 plus pi 2 equal to 0, identically, they are called zero-sum games. Why we discuss them separately? Because they have nice properties. They have very nice properties. So the zero-sum game as a definition, pi 1 plus pi 2 identically equal to 0. So in the matrix notation, we can say that the by matrix AB, you look at A plus B is all the entries are 0. AJ plus BAJ is 0. So there is a zero-sum game. So why it's important is that in the zero-sum game, their equilibria I can represent in an equivalent way, which is easier to find. For example, if you look at from player's point of view, player one's point of view, if he is playing a strategy X, so what is the least he can get? It is pi 1 of xy, you take minimum over y. We call it as m1 of y. Right? Sorry, m1 of x. So if I repeat, if as a player 1, he is choosing x, what is the minimum possibly he can get? That is m1 of x equal to minimum over y, pi 1 of xy. So that what you do, you choose an x dagger which maximizes this. So that is a max min. Basically, you are taking max over x, min over y, pi 1 of xy. So you call it as m1 dagger. Similarly, you can define max min payoff for player 2, that is m2 dagger. So this m1 dagger and m2 dagger are called max min payoffs for respectively players 1 and 2. And this x dagger and y dagger, where these max min payoffs are achieved, they are called max min equilibrium. Okay, max min strategies, and the pair x dagger y dagger is called a max min equilibrium. So now we have very important result for zero-sum games, which shows that for a zero-sum game, there are three things I am saying here. One is that a strategy profile is a Nash equilibrium if and only if that is a max min equilibrium. And as a consequence of that, what you are getting, any Nash equilibrium of the game will yield the same payoff for the players. And not only that, the sum of max min payoffs, m1 dagger plus m2 dagger is equal to 0. So what is the importance of that is that you look at the second one carefully, and also you remember, say, chicken game. The second game we had two equilibria. In one equilibria, the payoffs were 1 minus 1. In other equilibria, the payoffs were minus 1 1. So one equilibria is beneficial to player 1, other equilibria is beneficial to player 2. So the payoffs are different in different equilibria. But zero-sum game, that doesn't happen. So you can safely play any equilibrium you like, you will get whatever you are guaranteed to get, you will get. That's the advantage of that. So here, because of lack of time, I'm not going to further details, that m1 dagger plus m2 dagger equal to 0, what it means is that, you see, m1 dagger you substitute, what is that? It is max min over pi 1, and m2 dagger you substitute, it is actually max min over pi 2. But pi 2 is actually minus pi 1. So you club all that. What you can extract from this theorem is that what is called the minimax theorem, which says that for a zero-sum game, which we can represent now just by one matrix A, because B is minus A, it says that max min of pi 1 is equal to max min of min max of pi 2. I repeat, for a zero-sum game, which is represented by the matrix A, max over x, min over y, x a y transpose is actually min max. Max min and min max are same. So this was first established by John von Neumann in 1928. And of course, after that, there are many generalizations also. And the common value, which is max min and equal to min max, the common value is called the value of the game. So that is about the zero-sum games. And this topic of zero-sum game, the last thing I want to say is that this property that any equilibrium you can choose, you will get the same payoff, right? It's called the interchangeability property of Nash equilibrium. And these are not in general true for any game. Non-zero-sum game, this may not be true. So that is where in non-zero-sum game, whenever you have more than one equilibria, it's a difficult thing in general to decide which Nash equilibria is better. Of course, zero-sum game, that problem is not there. That is why I need to discuss what is called refinement of Nash equilibria. So before that, I will discuss how we can calculate a Nash equilibrium through nonlinear programming problem, which is the next slide. So this one, I think I will skip 2 slides because of lack of time. So we are skipping the nonlinear programming part, which essentially meant that Nash equilibrium we can also calculate using the nonlinear programming problems. That if you can solve nonlinear programming problem, you can actually use that to get the Nash equilibria. And in zero-sum case, we can make it equivalent to linear programming also. So that part we are skipping. Now we come to the refinements of Nash equilibrium. So as I have told, the refinements are necessary for non-zero-sum games because there may be multiple Nash equilibria and different Nash equilibria, different players may be more beneficial. So I will just explain one notion of refinement here, which is the so-called perfect equilibria. It is defined as an equilibria or a tuple, you see, or a pair X star Y star is called a perfect equilibria if I can approximate it through a sequence of profiles xk, yk. So these xk's, yk are coming from the interior of the simplex. Why interior? Because in interior, if you take xk, yk from the interior, xk's all components are present or active. That's why you are taking that. So what happens is that if you take a perfect equilibrium, we are not only testing it against y star. For y star, possibly some components are not active. So we are also testing it against yk, which is close to y star, but in yk, all the pure strategies are present. So that is the advantage of a perfect equilibria. And we have a theorem which says that every game has a perfect equilibria and every perfect equilibria is a Nash equilibria. So that's why it is a refinement of that. So this for more details, I'll refer to the book by Meyerson, Harvard University Press in 1997. And there are many other refinements of Nash equilibrium called proper equilibria and persistent equilibria, also stable sets and so on. Many are there. So very nice reference for that is a book by Van Dam, Stability and Perfection of Nash equilibria. So this will give all ideas about the refinements. And here I should also mention that, so for the contributions made by Nash and Harsanyi and Selton, they got the Nobel Prize in 1994 in economics theory. Here Selton's contribution was regarding the refinements of Nash equilibria, and Harsanyi's was in the study of incomplete information games. If the players don't know other players full information about their payouts, etc., what to do. So these three together got the Nobel Prize in 1994. So with that, I go to the next section about population games. So I have about, I think 7 minutes. So population games, what do you do? We don't assume that the players are actually rational here. So they are just, without much of rationality, they just start playing something. Either you are inherited and you act according to your inherited property, or you just to look around, you're a little bit myopic in your actions. So here I am taking only one population of individuals here. So that's why I am putting a symmetric game here. So a two-person game given by a pair AB, we call it a symmetric if B equal to A transpose. So in terms of pi 1 and pi 2, what it means is that pi 2 of xy, I can write it as pi 1 of yx. So all payoffs are represented by just one function pi 1. In other words, what means that the player role as a player 1, role as a player 2 is not important here. What matters is only what you do, x or y, what you choose. Accordingly, what you will get, pi xy or pi yx. So that is where we are looking at symmetric games. In a symmetric game, we can always find a Nash equilibrium of the form x star comma x star. That means x star is best against x star So it is symmetric. The pair, the strategy sets are symmetric for both players. So X star is best against X star. So X star, X star is an equilibrium. So we call that such an equilibrium as symmetric Nash equilibrium. So for symmetric games, symmetric Nash equilibria always exist. And I have a motivation slides here. So I think I'm going to skip here because we are approaching time. I think this one more scenario 2 also I have to skip. And I have to come to definition. So, now I define what is called a stable state. So we have a symmetric game defined by the matrix A, and we have a strategy X star. So X star is called a stable state if let me first tell what is algebraically what is that. If for every x not equal to x star, there is a p star which is a positive number lying between 0 and 1, such that E of x star comma px plus 1 minus px star is strictly greater than ex comma the same thing. What does it intuitively mean is that if almost all the members of the population adopt the same strategy x star, then if a mutation appears in the population, they behave like X. So mutation is coming in a small proportion P. Then that Px plus 1 minus Px star means the post-entry population, wherein little bit people are mutants and most of the people are the incumbent X star people. In that post-entry population, the incumbent behavior X star earns strictly higher. So such a strategy X star is called a stable strategy. It's called ESS in abbreviation. So there is a characterization for theorem for such equilibrium, such a stable state, which says that an X star is a ESS, stable state, if and only if two conditions are satisfied. One is that this X star is symmetric Nash equilibrium. That means X star is best against itself. Second condition is that if there is any other best response, then we have a second order condition saying that pi x star x greater than pi xx. So this is an equivalent condition. So every stable state is a Nash equilibrium, but the converse need not be true. In order for that to be sufficient, you need a second order condition. So that is the characterization theorem. For that, now we go back to the examples. In the hawk dog game example, if you go back, and we have seen that if you take v equal to 2 and c equal to 6, that 1 by 3, 2 by 3 was a mixed equilibrium. And that we can see in this case by the previous characterization theorem, we can verify that that is a stable state. Intuitively, what it means that if you have a population of birds who are playing like hawks and dogs with a given payoff matrix like -2 to 0, 1, then the stable state is that 1 by 3rd of the population should behave like a hawk and 2 by 3rd of the population should behave like a dog. So that is a stable state. Okay. So that is the stability. And so now I go to the next. We can actually go to rock paper scissors game, and we can show that in general there are no ESS in this game. You can use the characterization theorem and show that all the strategies are best response against X star, which is 1 by 3, 1 by 3, 1 by 3. And we can see that say denoted by E1, it's actually S1. S1 we cannot satisfy the conditions of the theorem, so there is no ESS in this game. So ESS need not exist always, but whenever it exists, it is nice. So next we have I think we have a theorem which gives the structure theorem for ESS, which says that now as a result of that, we can conclude that in a game of where we have n strategies, at most we can have n ESS and so on. And also if you have interior ESS, it is unique and so on, we can show. So next, we can show that if xt is an ESS, Then there is one more characterization in terms of neighborhoods of X star. It says that X star is an ESS if and only if in a neighborhood y comes from a deleted neighborhood of X star, we have that pi X star y greater than pi y y, and this will actually help in proving many other things. So now I will skip a few slides and go to my final conclusions. Okay, so because of lack of time, so I skipped some slides, but it whatever I wanted to convey, I am conveying. So I'm very happy about that. So for what I have done, so I have defined what a game is. We have seen few examples, motivating examples, and what is the relevance of Nash equilibrium. And I explained why in pure strategies there may not be always Nash equilibrium. So we have to go to mixed strategies by convexifying our strategy set. Then by Nash theorem we have existence of Nash equilibrium. Then we also seen that for zero-sum games, nice properties are there. You can play without worrying about other player. You can use your max win strategy always. But then non-zero-sum games we have difficulties, so we have to talk about refinements of Nash equilibrium. Then the refinements of Nash equilibrium is only one way of refining. Then there is also another way of population way of thinking. So what I have, in that we have defined what is called evolutionarily stable state. That is another way of biologically thinking about refining Nash equilibrium, because we have seen that every stable state is a Nash equilibrium. So that is another way of thinking about that, and it also has the stability, a lot of stability properties. So it can be connected with what is called a replicator equation. The ESS is actually called dynamically stable properties. Also, one can show. So overall, what I am showing is that the concept of equilibria is very crucial in game theory, and the concept of refining that is also very important, and it has also can be approached through the stability of population states, and also it can be done in more dynamically way using the theory of differential equations and Lyapunov stability. And many other topics in game theory I have not touched upon in this game. Few of them are like the theory of games with the continuous strategy spaces, where in economics there are many games where each game has a continuous strategy space. Not just the pure strategies are S1, S2, S10 are discrete. So for example, the famous Carnot duopoly, which they studied even in 19th century itself. So there we have to see which is your optimal production we have to do. It's a real number you have to choose from an interval or from the real numbers. So that there are many games in economics where strategy sets are a continuum that we have not touched upon. Also, there is games in extensive form where games can be represented in as a tree, which we see tree in the discrete math or graph theory we see. We have not touched upon that. Also, there is a cooperative games or coalitional games. Another Nobel Prize in game theory economics was related to that in Shapley and Roth. They got Nobel Prize in 2012 for their work in design of market and cooperative games. So the cooperative games is another important topic, and dynamic games, where you talk about dynamic games using discrete equations or differential equations, so-called perturbation games, which is very important in military applications. Then games with incomplete information. So that is where the Harsani's contribution, he also got Nobel Prize, as I mentioned earlier. Then finally, the games and learning. So nowadays it's learning, online learning. It's it's receiving a lot of attention in that. So games where players are not 100% rational, they keep playing, they're learning from what their experiences, then update their strategies. So there are a lot of material on games and learning. So finally, my references. So all these references are bibliographical in nature, in the sense that they give a lot of bibliographical sketch also. So finally, I end by bowing in front of the memory of Ramanujan. And as he said, an equation means nothing to me unless it represents thought of God. So for me, I understand this way, like it shows the devotion of Ramanujan to mathematics, especially in number theory. So with this conclusion, so I once again thank the organizers for giving me opportunity, and I thank the chair for his kind words about me. Thanks. Thank you very much.
Saiju, for such a wonderful presentation. I hope many people have learnt a lot from your presentation. There is one question coming for you.
Yeah.
So, is there any characterization of ESS in terms of perfect equilibrium?
I don't know about that. I am not aware of that. So right now, my answer is that mostly no, because I am not aware of that. But maybe with the epsilon probability, maybe there, but I am not aware of that. In terms of perfect equilibrium, because mostly perfect equilibria, the real motivation comes from the theory of extensive form games. That particular type of refinement is coming from there. So it is characterization in terms of perfect equilibria. Actually, I am not aware. So I hope that it is not there. But if it is there, I would like to know. Please, anyone, if anybody knows about that connection with perfect equilibria and ESS, please do drop me an email. Thanks.
This question is asked by Professor Vetrivel.
Yeah. Okay. Thanks. Any other question?
Other questions? Right now, there is only one question for you. We'll just wait for 1 or 2 minutes if anybody wants to.
Yeah, sure.
Your hawk and dove example was on the spot. With probability 1/3, you should behave like a hawk, and with probability 2/3, you should behave like.
Yeah, that is real life.
Yes.
Real life, yes.
Really interesting. I think no other questions are coming.
Yeah, that's fine. Thank you.
That was really a wonderful talk. And 1 minute.
So thank you, Professor Saju, for the talk. I also thank Professor Nilesh for chairing the session. Now we have a second invited talk by Professor Krishnendu Vaisar Mohali. I request Dr. Abarmayan to introduce the speaker to the audience and to chair the person.
Thank you, Ramesh. So following the talk of Shaiju, we will now have talk of Professor Krishnendu Gangopadhyay from ISER Mohali. So he is broadly interested in hyperbolic geometry, group theory. So it does seem that there is an overlap that I have with him, at least in terms of symmetric spaces of non-compact type, at least of rank 1, and general Lie groups. So he finished his PhD in IIT Bombay under Ravi Kulkarni. So since 2010, he has been at ISER Mohali, and so today he will talk to us about reversibility in groups and geometry. So with those few words, I invite Krishnendu to give the talk. Krishnendu, you're not audible to me, at least.
Now, am I audible?
Yeah, now you are. Thank you.
Okay. Is it okay?
Yes.
Okay. So what I am saying that it's nice to hear you after a long time. Maybe you can switch on your camera for a minute so that I can see you after a long time. I also enjoyed your talk when you gave at ISER Mohali around a couple of years back. All right. Yeah. Hi. Yeah. Great to see you. Okay. So what I will do now, I will share my screen. So let me see how to do that. So let me share my entire screen. That's better. So yeah. So okay. Okay. So you can see my screen, and here is my where is okay. So view full screen mode. Yeah. So can you see it?
Yes. Yes.
Okay. So you see, while I am lecturing, I cannot see the camera, but in case there is any issue, please stop me and let me know. All
Yeah,
right?
I will let you know. Yes.
Yeah, please. Okay, so I thank Ramesh and colleagues from IIT Madras for this invitation to this national symposia on mathematics and its applications. It's an honor to speak in such a symposia which is held in memory of Srinivas Ramanujan and the occasion of the National Mathematics Day. So I really thank you for giving me this opportunity. So now, as you can see, that I will be speaking about reversibility in groups and geometry. So this talk is partly based on my joint work with a student, Tejbir Lohan, and with a postdoc, Dr. Chandan Maiti here. But before that, I will try to cover a considerable background so that you get a feeling for the problem. Oops. Yeah. So my slide is moving, right?
Yes, it is.
Yeah, thanks. So let G be an abstract group. You start with any abstract group. An element in capital G is called real or reversible if it is conjugate to its inverse. And an element in a group G is called an involution if it is a order 2 element. Now it is sometimes curious to know when G is a product of two involutions in G, and when G is a product of two involutions in capital G, it is called strongly real or strongly reversible. Now, some authors have also used the terminology bireflexional because of the motivation from symmetric spaces or classical geometries where involutions appear as reflections in a line or a plane. All right, and one would like to see every element, every rigid motion, for example, as a product of two reflections. Now we will mix up these two terminologies. Sometimes I will call them real, sometimes I will call them reversible, and similarly strongly real and strongly reversible. I will mention shortly why this term. There are two terminologies of the same kind of object in mathematics. It is because they appear from different viewpoints, and depending upon the viewpoint, people have called them either real or reversible, or many other name also, but these two are most common names. Now here is a quick observation. Suppose you have a element in the group capital G which is a product of two involution, then it is immediately you can see that it is conjugate to its inverse by an involution, which means every strongly real element is real. Okay, but the converse is not often true. All right. So, but the converse is true if G is conjugate to G inverse by an involution. So when this element H, the conjugating element H is an involution, then you can see that G is the product of two involution, hence G is strongly real. All right. But in general, not every real element is strongly real. Now, here is the broad theme of research which is scattered around literature from many point of views. So the main problem is to classify real and strongly real elements in your favorite group G. And if suppose G is not strongly real, then find out the minimum number of involutions which is needed to express G as a product of involutions. And there is a notion of involution length of a group, which is the supremum of all involution lengths of individual elements. All right, but in this talk I will mostly focus on the first problem, the classification of real and strongly real elements, but the other two elements are also related, and they are interesting in their own rights. Now here is a very basic example. Okay, so let's start with very basic finite groups, Q8, which is just a group generated by 8 elements, plus minus 1, plus minus I, plus minus j, and plus minus k, where I, j, k are, as you know, generalized complex numbers, or as they call it, unit quaternions. Now, it is easy to see that every element of Q8 is reversible. Just conjugate I by j, and that will give you reversibility. But plus minus 1 are the only strongly reversible elements. Okay. Next, consider the dihedral group. Okay, so there are two dihedral group. One is dihedral group of 2n generators. Two generators R and S, where R square equal to S square equal to identity, and Rs to the power n. I mean, these are the defining relation for the dihedral group. So these are group in a in a polytope of symmetric polytope of 2n faces generated by reflections. And there is this infinite dihedral group, which is just generated by two reflections in any plane or any polytope. All right. So now one can easily see that if you take an element from the infinite dihedral group, then it is of this form. It is a binary string of R and S, like the one I have written here. Okay. Now you start with G of this form. You start with R and then S, R, S, like it's like a computer string with +1 -1 binary coding. And then G inverse is easily seen to be equal to R times G times R. Now, since R is the involution, it shows that G is strongly real. Now, this shows actually every element of the infinite dihedral group is strongly real. And since there is a surjective homomorphism from D infinity to D2n, every element of D2n is also strongly real. That means the product of order 2 elements. So there are groups where every element is a product of 2 involutions, and then there are groups where not every element is a product of 2 involutions. One can also show that every element in the symmetric group is also strongly reversible. So for finite groups, in some finite groups, one can actually see that which groups have this property where every element is strongly real, and more or less such groups are well understood. Now, the motivation for reversibility appear naturally in different areas of mathematics or science. For example, if you look at the motion of a pendulum or any dynamical system or any geometric motions, it's a natural problem when a motion reverses its direction or reverses its, motion. All right. So reversibility occurs very naturally in different areas of mathematics, but from the viewpoint of group theory, reversibility occurs while studying representation theory. Now, it is pretty well known that for a compact Lie group, G is conjugate to G inverse if their irreducible characters are conjugate to each other. Now, it's a classical theorem of Frobenius and Schur from 1906 that the reversible conjugacy classes of G, that means those conjugacy classes which contain both G and G inverse, that is equal to number of real valued, so number of reversible conjugacy classes of G is equal to the number of real valued complex irreducible characters of G. And this gives the motivation to call them real when you look from a representation theoretic or group theoretic point of view. Now, when you look from geometric point of view, which I will mostly describe, it is more natural to call them reversible. I will tell you why. Okay. Now, the point is, it's a problem which is scattered around different areas of science from different perspectives, and it's a natural problem to study, to classify such elements. Now, for a nice exposition of this problem from mostly geometric and dynamical viewpoint, one can look at this book by Anthony G. O'Farrell and Ian Short, which was published by London Math Society in 2014. So this gives you a nice exposition of up-to-date research work until 2014. Now, in spite of many works in this topic, a complete and concrete classification of real and strongly real elements in a given group is known only for a very few families of groups. Mostly people have worked with finite groups because of these two basic examples. I mean, it's natural problem to find out groups where every element is real, to find out groups where every element is strongly real. Now, for finite groups, there are many work. The literature is full of work in this direction, and still, I mean, there are works coming out, and the situation is well understood, more or less. Okay, so T.F. and Zaliski, for example, classified finite quasi-simple groups where all elements are real, and following this work, several authors have investigated strong reality also, though the picture is not completely known, but to a large extent, there are many things which are known. But our interest is not finite group. We are interested in infinite groups because those are the group which mostly appear as automorphism of geometric spaces. Now, mostly for infinite groups, people have tried to find out the converse question. Okay, so they have tried to answer the converse question: when does a real element is strongly real? So there are several authors which is associated to this problem, like Ehlers, Unenberger, etc. But not so long back, Anupam Singh and Manish Thakur, they studied this problem in for semi-simple elements in a semi-simple algebraic group, and they proved the good characterization of when these two notions are equivalent in a connected adjoint semi-simple algebraic group over a perfect field with certain conditions. Now, essentially, what their work implies that in most classical groups over a field, a semi-simple element is real if and only if it is strongly real. Now, an exceptional class in this family is the symplectic group, where there are real elements which are not strongly real. Okay, and Singh and Thakur mostly worked with semi-simple elements, and they did not say much about unipotent elements. So they did not say much about elements which have eigenvalues only one when you consider them restricted over matrix algebraic groups. Okay. Now, other than the characterization of the above type, concrete classifications are known only for a very few families of groups. Now, today we will describe a few families where complete classifications are known, and those are the isometric groups or in classical geometries. Now, I do not want to give a very detailed introduction to classical geometries, but I would just like to point out that there are essentially three types of geometries that classically one can see in the scientific literature. So the symmetric spaces, which Opromeyan mentioned, are generalization of these three classical geometries. So these three classical geometries are the Euclidean geometries, which is given by the Euclidean affine plane, Rn equipped with the Euclidean metric. Now, a line in a geometry is a distance minimizing curve. And in Euclidean geometry, which we are very familiar, lines are the so-called straight lines. All right, that means the curvature is zero in this geometry. And the triangles, you can express this fact by using comparing triangle. So triangles are such that the sum of the angles of a triangle is equal to pi. And the isometric group is given by the semi-direct product of the orthogonal group and the Rn, the full vectors. Okay, so and these are the isometries. X goes to X plus B, where A comes from an orthogonal group and B is just a vector in Rn. Then you have the spherical geometry, which is the geometry on Sn equipped with certain metric, which I don't want to get into. But spherical geometry is essentially, a compactification of the Euclidean geometry by stereographic projection. And one can see accordingly that the isometric group of the spherical geometry of the sphere as a geometric space is just the orthogonal group. So you just remove the translation part from the Euclidean isometric group. What remains is the isometric group of the n sphere. But the geometry is somewhat different because it's non-Euclidean, and some of the angles of a triangle is greater than pi, and the curvature is constant, +1. Now there is this negatively curved geometry based on which the symmetric spaces are mostly modeled upon. So this is the hyperbolic geometry. So this is given by the unit disk in Rn+1 equipped with this special metric. Okay, and one can see that the boundary of the hyperbolic space is the n-1 dimensional sphere. Now, lines are semicircles orthogonal to the boundary or the diameters of the disk, and isometries we will define later because we will give you a result of classification of reversible and strongly reversible elements in this geometry. Now, what I can say here that in dimension 2, many students might have studied them while doing a complex analysis course. These are given by the Mobius transformation. Z goes to Az plus B by Cz plus D, and this geometry is implicit in things like Schwartz lemma or the classification of automorphisms of the unit disk. Okay, so these are the those are essentially the classification of isometries of the disk model for the hyperbolic plane. All right, now this geometry differs significantly from Euclidean geometry. So, for example, some of the angles of the triangle is less than pi, and most importantly, given a line L3 and a point not on it, there are several lines which passes through that point and which are parallel to the given line. So this differs significantly from Euclid's fifth postulate and is a nice model for a non-Euclidean geometric setup. So this was a brief introduction to classical geometries. Now I will discuss about reversibilities in classical geometries. Now I will start with the orthogonal group, the group ON and the SON, the orthogonal transformations with determinant 1. Now it is easy to see that it's essentially a matrix computation that if you take O2, the group of all rotations and reflections in a plane, then it is easy to see that every element in O2 is reversible. However, if you take this rotation cos theta minus given by this matrix cos theta minus sin theta cos theta, then G cannot be conjugated to G inverse in the group SO2. So even if G is reversible in O2, G is not reversible in SO2. So reversibility becomes subtle in special subgroups of a given group. Okay. Now this example one can generalize to higher dimension, and not only that for orthogonal groups over arbitrary fields of characteristic 2, not 2. And Unenberger, for example, have studied reversibility in orthogonal groups over fields. And from that work, it follows that every element in ON is strongly reversible with the product of two involution. But this is not the case in SON, as we have seen. Now, there is a work, again, they did it over arbitrary fields, but I have only stated here for SON, that an element in SON is strongly reversible if and only if when n is not equal to 2 mod 4, or if n equal to 2 mod 4, then an orthogonal decomposition of Rn into orthogonally indecomposable subspaces contains an odd dimensional summand. So in that case, T is strongly reversible. All right. Yeah. So in that case, T is strongly reversible. Now, one can also note that an element T in SON is reversible if and only if it is strongly reversible. So combining these two work, it essentially it completely classifies the reversible and strongly reversible elements in SON. And this gives you the reversibility of isometries in spherical space forms. Now, one natural question to ask it for Euclidean space form, where the isometric group is, as a group, it is a semi-direct product of two groups. One is ON and the other is the affine group RN, right? So it's a semi-direct product. And Ian Short studied this group, and he proved that every element of isometric group of En is strongly reversible. Now, what about the question in the identity component? So there are counterexamples that not every element is strongly reversible in this group, and Short actually proved that an element in this identity component is reversible if and only if it is strongly reversible. And then he classified completely the strongly reversible elements. Now it's a complete classification. So there are different cases based on whether n equivalent to odd a odd number, zero, not odd number, n equivalent to 0 or 3 mod 4, or n not equal to 0 and 3 mod 4. Now the punchline is that when n is equivalent to 0 and 3 mod 4, then every element in this identity component is strongly reversible. But when that is not so, there is a complete classification, which I am not giving the details, but you can see it from the slides. I mean, he classified them completely in this Euclidean setup. Now, what remains is the hyperbolic setup. Now, that's what I will discuss now. Now, to discuss that, I will use a linear model for the hyperbolic geometry, which is given by this Lorentz orthogonal group. So you start with this matrix J, where only one diagonal entry is 1 and the rest of the entries are +1. Then you have this Lorentz orthogonal group, ON, 1. Now, these groups preserves the bilinear form of signature n, 1 on Rn plus 1. Now, the hyperbolic n-dimensional space is just a component of the conic given by the sphere of radius -1 under this bilinear form. Okay, so normally we take the conic where the first coordinate is always positive. All right, so this conic is two hyperboloid, one on the upper half space and one on the lower half space. So we take the hyperboloid on the upper half space as a model for the hyperbolic n space. And there is a natural metric, which is just the negative of the inner product, cosine inverse of the negative of the inner product. So that gives you a matrix that makes you this Hn as a metric space, and one can see that they satisfy, and they are isometric to the earlier hyperbolic space that I defined. All right. So now I will work with this model where the isometric group of the hyperbolic n space is given by 2 out of the 4 connected components of the Lorentz orthogonal group ON, 1. And we denote it by PON, 1. All right. So now it follows from many works in the literature that every element in PON, 1 is a product of 2 involution. But what about strong reversibility in the identity component of P1, 1? I mean, the component which are the which contains the identity, or which are the orientation preserving isometries of Hn. Now, I will demonstrate the subtlety using the 2 and by mentioning the 2 and 3 dimensional cases. Now, consider when n equal to 2. Then the identity component can be identified with the group of 2 by 2 real matrices, SL2R, modulo ±1. All right. And the hyperbolic 2 space can be identified with the complex upper half space. Now, this group SL2R acts on the complex upper half space by isometries, and they are realized by this Mobius transformation. Z goes to AZ plus B by CZ plus D. Now, if you look at the action of the translation, Z goes to Z plus 1 on the boundary of the hyperbolic space, which is the real line, then you see that the direction of Z goes to Z plus 1 on the real line is different from the direction of Z goes to Z minus 1, which is its inverse. All right. So now, since real line is a single line and there are only 2 orientation, I mean, an isometry which do not respect the orientation, cannot be conjugate to each other. Two isometries are which respect different orientation of the real line cannot be conjugate to each other, because conjugation is essentially change of viewpoint of two isometries, and the geometry does not change there. So T, this translation T, is not conjugate to its inverse in PSL2R. So accordingly, there are elements in SO0 2, 1, though they are conjugate in the full isometric group, they are not conjugate in SO0 2, 1. Now come to the case n equal to 3, where again we can identify the isometries by Mobius transformation of the entire complex plane. So the Riemann sphere, the extended complex plane, can be realized as a boundary of the hyperbolic 3 space, and the isometries act as Mobius transformation of the boundary. Now, it's a classical result of Fenchel. He exploited this action to prove that every element in SO0 3, 1 is a product of two involutions. All right. So in SO0 3, 1. So every element of SO0 3, 1 is strongly real. Now, this shows that reality and strong reality can be very different in different dimensions and in different subgroups of the same group. Okay, so it required a subtle understanding of the general dimensional case. And in a paper in 2011, this problem was investigated by me, and I gave a complete classification of reversible elements in SO0 n, 1. Again, here it depends on whether n equivalent to 0 mod 4 or 3 mod 4. So for n equivalent to 0 and 3 mod 4, it was proved that every element is strongly real, every element is real, but in the other cases, it required a finer analysis. Okay, now this gives you a classification of real elements. And one can also prove that in SO0 n, 1, an element is real if and only if it is strongly real. That means an element is reversible if and only if it is a product of two involutions. All right, so the above theorem also classifies strongly reversible elements in SO0 n, 1. Now, the example I gave you for PSL2R, that might have already given you the feeling why the terminology reversible has also been used in the literature. All right, because reversibility means essentially, the directions are whether under conjugation the orientations are getting reversed or not. So the motivation comes from dynamical system, but we will use both the terminology real and reversible. Now, this was the case of the classical hyperbolic geometry. Now, in rank 1 symmetric spaces of non-compact type, there are two more hyperbolic geometries, one over the complex number and one over the quaternions, where the isometric group appear as isometric group is given by linear transformations. Okay, so one is complex hyperbolic geometry and the other is quaternionic hyperbolic geometry. Now, in 2013, in a joint work with John Parker, we have classified reversible and strongly reversible in reversible elements in complex hyperbolic geometry. And in 2020, with a postdoc Eliasar Mohali, Sushil Bhunia, we have classified reversible and strongly reversible elements in isometric group of the quaternionic hyperbolic space. Now, there is one more symmetric space of non-compact type, which is still remaining, which is the exceptional type, the Cayley plane, but there the isometric group is not easily given by linear isometries, and we have not studied that yet, but that case is still open. But except that, in other rank 1 of symmetric spaces of non-compact type, reversibility problem of isometries has been settled by this series of works. Now, we have discussed reversibility in Euclidean geometry. Now, a natural problem to ask it for Hermitian isometries. I will mention what do I mean by Hermitian isometry. So you start with the field of complex numbers or the skew field of quaternions. Now consider the affine n space over F and consider this positive definite Hermitian form. Okay, the unitary group is given by linear transformations which preserve this Hermitian form. In matrix notation, they are given by matrices where G bar transpose G is identity. Now, under usual notation, UN, C is the usual complex unitary group, and over quaternions it is denoted by SPN. Now, these are compact subgroup of the general linear group over F. All right, and Hermitian isometries are given by semi-direct product of this compact group with Fn. But before proceeding further, let me just recall what is the skew field of quaternions. So it's a four-dimensional real algebra generated by, 1 and 3 kind of generalized complex numbers, I, J, K. It is a right vector space. Now, you consider a right vector space over the quaternions. So we have to specify whether we are taking multiplication from the left or from the right because of the non-commutativity of the quaternions. And accordingly, one can define what is the right linear map, and one can represent it by a matrix over the quaternions. However, the complex linear algebra does not carry over immediately to the quaternions because of the simple fact that there is no well-defined conjugacy invariance over the quaternions. For example, if you take a eigenvalue lambda and an eigenvector v of a right linear transformation, then one can see that v mu is also an eigenvector but corresponding to a conjugate eigenvalue to lambda, which is mu inverse lambda mu. So therefore, eigenvalues of a quaternion linear transformations occur in similarity classes. And this actually completely breaks down the notion of characteristic or minimal polynomial, the well-known conjugacy invariance over complex number. And one has to sort of take care of this fact while studying quaternionic linear algebra. Now, take a right vector space of dimension n over f, and you give it the usual metric, the Euclidean metric. Then that's kind of generalized Euclidean space over complex number or the quaternions. And the isometries are just given by, like Euclidean isometries, I mean, they are given by affine transformations, x goes to x plus b. And one can identify it with the semi-direct product of the unitary group with Fn. Now, one can ask how to classify reversible and strongly reversible elements in this group. This would generalize Short's result in this setup. Now, in a joint work with my student, PhD student Tejbir Lohan, we have classified strongly reversible elements in UNF semi-direct product Fn. So we have proved that an element in this group is strongly reversible if and only if the linear part of G, that means the part which is contained in the unitary group, is also strongly reversible. And about reversibility, there is a slight difference over quaternions and over complex number. So if you take every element in SPN semi-direct product Hn, then every element is reversible. But when you take an element in UN semi-direct product Cn, an element is reversible if and only if it is strongly reversible. So not every element is strongly reversible. It is strongly reversible if and only if it is reversible. Okay. And here is a simple example. So one can further ask it for SUN semi-direct product Cn, and here is the example in SU5 semi-direct product C5. So just take this element A, which is given by this diagonal matrix, and consider the vector V, which is the first four entries 0 and the last entry is 1. All right. So then A is strongly reversible in SU1. It follows from earlier works. But assume G is strongly reversible in SU5 semi-direct product C5. Then by following these relations, H inverse equal to G inverse and H square equal to identity, one gets certain set of equations, and that will imply that every element, if you take a reversing, if you take a conjugation element which is given by this linear transformation B and another vector, say W or U here, then B will be of this form. Okay. So now that will lead to a contradiction, because determinant B will be -1. So if we start with a element of the type AV that I stated, then if you assume that it is strongly reversible, then that element does not come from SU5 semi-direct product C5. So not every element in the determinant 1 component of the affine group is strongly reversible. So one has to classify them. Now, to classify elements in SU1 semi-direct product Cn is a tricky problem, and we have answered the question completely in the following theorem. So we have proved that, again in a joint work with Tejbir, that if you take an element in SU1 semi-direct product Cn such that its linear part is strongly reversible, then the element from the Hermitian isometry G is not strongly reversible if and only if up to conjugacy of G it is of the form A comma V, where A is just this diagonal element and B is a vector of this type. Okay, now all elements G which are not of the above type are strongly reversible in SU1 semi-direct product Cn. So this completely classifies strongly reversible elements in SU1 semi-direct product Cn. All right. So there are real elements in SU1 semi-direct product Cn which are not strongly reversible, but one can classify exactly which real elements are strongly reversible, and this theorem mentions that. All right. So this completes the picture for Hermitian isometries. Now, in the next few minutes, I will be talking about my joint work with Chandan Maiti, where we have asked this problem for unipotent elements in a classical Lie group. All right. So this is a joint work with Chandan Maiti. Now, what we are asking here, that from whatever I have described so far, that from my work and from the survey of Jansort, that concrete classification for reversible and strongly reversible elements are known only for the following types of groups. So the compact groups, ON, UN, and their determinant 1 components, and SPN, which is very recent, and the general linear group, GLNR and GLNC. Even for a special linear group, a concrete classification for reversible and strongly reversible elements is not completely well understood. So in an ongoing work, we are trying to understand that, but it is not known completely. And then you have the isometric groups of the Euclidean space and the Hermitian isometries that I have spoken, and the isometric groups of rank 1 symmetric spaces of non-compact type. So concrete classification, that means a list of real and strongly real elements are known only for these groups and for finite groups of simple and quasi-simple type. Now it's a natural problem to ask it for other families of Lie group. All right. Now, in finite group theory, reality of unipotent elements in finite groups of Lie type has been investigated by TF and Zaliski in 2004. Now, in this work, we initiate this investigation for classical Lie groups. So to understand Lie group, one has to look at the Lie algebra, which is the infinitesimal version of a Lie group, which is the tangent space at identity of the Lie group. And okay, we have used this Lie algebra setting in order to understand real elements of unipotent elements. Now, what we have done, we have used the adjoint representation of a Lie group. Okay, so you take a Lie group, then there is an adjoint representation that gives you a representation of the Lie group to the general linear group of the Lie algebra, okay, which is the automorphism group of the Lie algebra. Now, for an element x in the Lie algebra, the adjoint orbit of x is just given by the image of the adjoint representation, image of X under the adjoint representation by this orbit. Now we generalize the notion of reversibility or reality in the Lie algebra setup using this adjoint representation. So an element in the Lie algebra X is called adjoint real. We denote it by add suffix capital G real to mention that capital G is the Lie group whose Lie algebra is script G. So an element is called adjoint real if minus X belongs to the same adjoint orbit. And an adjoint real element is called strongly adjoint real if minus X and X are related by an involution from the group G by the adjoint representation. Now I must say here, this notion is very general, but if you restrict yourself to matrix group, then the adjoint representation is just the usual conjugation of capital G on script G. All right. So you can see that essentially what we are saying, that if capital X and minus X are conjugate to each other by an element of capital G, in case G is a matrix Lie group, then we are calling that strongly adjoint real. So this generalize the this gives you an infinitesimal version of the classical reality and strong reality for Lie algebras. Now there is an exponential map of a Lie group, which is from the Lie algebra to the Lie group, which is in general a local diffeomorphism, and it may not even surjective. Okay. Now we have proved a small lemma that if you have a Lie group, then for a element X in the Lie algebra, if it is adjoint real or strongly adjoint real, then corresponding element in the Lie group under the exponential map is real or strongly real. Okay. Now it is also a result that the unipotent elements in a semi-simple Lie group are exponential. That means the exponential map is a diffeomorphism on the unipotent, from the nilpotent component of the Lie algebra to the unipotent component of the Lie group. Okay, so this helps us to understand the unipotent elements of the reversibility of unipotent elements of Lie group by studying the reversibility of nilpotent elements in the Lie algebra. Okay, so the reversibility or reality of the unipotent elements in the Lie group G are determined by the adjoint reality of the nilpotent elements in the corresponding Lie algebra, and this is the key. Okay, now for a classical simple Lie group capital G, we have classified the corresponding nilpotent elements in the Lie algebra, and then using the exponential map, this gives us a classification of real unipotent elements in capital G. Okay, so these correspondence we have used throughout. Now here is the list of simple Lie groups and their Lie algebras that we have considered in this problem. So there is a large family. Maybe I just zoom in. So there is this special linear group. So all these types, AN, BN, CN, DN. There is this classification of semi-simple Lie algebras. So these matrix group essentially represents them. And we have considered unipotent elements in each of these groups and have classified the nilpotent, reversible and strongly reversible nilpotent orbits in this group. And by exponential map, that gives you the classification of reversibility in the corresponding Lie groups. Okay, so let me not give you the details of the Lie groups, but they are actually, some of them appear in rank 1 symmetry. I mean, I think all of them appear in the rank, all of them appear in the theory of symmetric spaces. Okay, so rank 1 is only a special type, but there are higher rank symmetric spaces. Now all these groups appear as isometric groups of higher rank symmetric spaces. And I must say here, we have only considered unipotent elements in these groups, and have classified reversible and strongly reversible unipotent elements. Now, the classification of semi-simple element is tricky because the exponential map is not very well behaved like the unipotent component. Okay, and it may not be even subjective. So the same ideas may not be immediately carried over to the semi-simple case, and one has to do case-by-case analysis. Okay, so semi-simple case we have not done yet for all these groups. Only for SLNC we are currently investigating the semi-simple. I mean, we have a classification of reversible and strongly reversible elements in SLNC also. So for the semi-simple and semi-simple elements, it was more or less well known. But for general elements, we are hoping that we will give a classification of reversible and strongly reversible elements. All right. Now, what sort of techniques we have used to understand the reversible and strongly reversible nilpotent orbits in the Lie algebras? So there is a very well-defined theory of nilpotent orbits in semi-simple Lie algebra. So we have used certain tools from that theory, which is essentially comes from the thesis of Dr. Chandan Maiti, who wrote it under the supervision of Pralay Chatterjee from Institute of Mathematical Sciences, Chennai. So so his thesis gave us the motivation and provide some of the tools to work on this problem. And we have classified the reversible and strongly reversible elements completely using these tools. So I will not make it too technical, so I have not mentioned much detail about the key tools, but this paper is available on the archive. So if someone is interested, he can look into. Now, in the final maybe 2-3 minutes, I will mention another side work that we have done. That is for the group of n by n upper triangular matrices in GLNC. Now, I must say here that when we are classifying unipotent elements or nilpotent elements in the Lie algebras, we have chosen the whole group. Okay, so for example, in SLNC, we have exhibited conjugating element from SLNC, okay, which may not be necessarily nilpotent or unipotent. But one can ask finer question, that you restrict yourself to the group of all upper triangular matrices in GLNC. And then this notation is bad, but UNC here means the elements of T, N, C with 1 as a diagonal, the unipotent upper triangular matrices. Okay, that means only you have upper triangular entries and the lower triangular entries are all zeros. Okay, now it is well known that the number of conjugacy classes in this group T and C, okay, is infinite. So it's not the Jordan canonical form. So you may so when you do Jordan canonical form, you do conjugation inside GLNC. Now one can see in the literature that you may have the same Jordan form, but when you project it into the group T and C, that same Jordan form breaks into different conjugacy classes. All right. So that makes the problem, conjugacy problem, more complicated in T and C. Now, yeah, okay. So that's what I was telling, that so you may have a single Jordan form JG, but there are infinitely many conjugacy classes in T and C corresponds to JG. Now here we can assume n greater than equal to 6, because for n greater than equal to 5, one has a complete list of conjugation elements in T and C. Now here is a special problem, that classify reversible and strongly reversible conjugacy classes in this group of upper triangular matrices. And now, as I recall again, UN, C in this slide consists of the unipotent elements from T and C. That is, elements of T and C with 1 as a diagonal. Now one can prove using different methods. So with Chandan, we have proved it using a different method. Now it also follows from a very general result of Pralay Chatterjee and Slovic using completely matrix theoretic computations also. He has proved the same result, that there is no reversible element in this group UN, C. So if there is no reversible element, there is no strongly reversible element. So for UN, C, it is the final answer. Now, what about if you slightly enlarge the group UN, C? So in the literature, they have considered this group U plus minus N, C, which consists of upper triangular matrices with diagonal entries +1 or -1. Now, Slovik, using matrix theoretic computations, he exhibited several kind of reversible elements in U plus minus N, C. But for strongly reversible elements, he did not say much. And with Chandan Maiti, in a short note, we have proved that an unipotent element in U plus minus N, C is reversible or real if and only if it is strongly real. Okay, but we are talking only for unipotent element in U plus minus N, C. We don't know complete classification of reversible element in U plus minus N, C because as you can understand, I mean, there are infinitely many conjugacy classes, and it is not very clear how to tackle this problem in this setup. Now, we restrict ourselves to the unipotent elements, and we prove that an unipotent element is real if and only if it is strongly real. Now, what we expect is the following result, that every unipotent element in U plus minus N, C is strongly real. We expect that this should be true, but we have not been able to prove it. So I raised it here as a conjecture that every element in U plus minus C is strongly reversible. Now, on the other hand, I mean, there are several algorithms in the literature, like Beltiski's algorithm, where they have tried to understand conjugacy classes in the group of upper triangular unipotent matrices. Now, using that algorithm, Chain et al., Chain and his co-authors, has obtained certain canonical form for nilpotent orbits under the action of T n, C. Now, if we check each of these canonical form, we can check manually that they are all strongly reversible in U plus minus N, C. Now, Chain et al. Have done it, I would say, I should have mentioned here, not for arbitrary N, but they have done it for in up to 8. All right. So for up to 8, we can check manually that these are all strongly reversible elements in U plus minus N, C. But that does not answer the question because, even we can check manually. I mean, there may be other canonical forms as you grow, as N grows. And we really do not know, I mean, how to assert that or how to prove that every unipotent element in U plus minus is strongly reversible. Okay, so this question is still open and we don't know how to answer it. Okay, so with this, I would like to thank you for your attention.
So, on behalf of all of us, we would like to thank you, Krishnendu, for a rather lovely talk. Perhaps before I look for other questions, I have one sort of comment on this.
Yeah.
Since you did mention the relation in the compact group setting,
yeah,
of reversibility with characters being conjugate,
right?
One does wonder, because you're looking at nilpotent, so you're looking at adjoint orbits here.
Yeah.
That it might be tempting to look at representations. So the consequence of this reversibility on representation theoretic questions, because of course, for some group, like let's say Heisenberg group, for just an example, we know that these co-adjoint orbits actually give you everything, right? So all unitary irreducible representations do arise from such orbits. And so I just wonder in a speculative fashion whether this reversibility has a consequence on this, and perhaps so that's the comment I wanted to make.
Oh, that's a very I would say useful and very well thought comment. So I really thank you for that. I will definitely think about it. Yeah.
So let's see if there are other questions. It does not appear to me that this is the case. So I will take the opportunity to thank you again for
Thank you.
nice little talk, and I hope you do stay for some of the other talks too.
Yeah, so that's what I was about to make a comment. So I am very sorry that I will not be able to stay for the other talks because we have a meeting at ISR Mohali from
I see.
2:30 that I am supposed to attend. So it's
Understandably.
a
Nonetheless, we thank you for making it here and giving us the nice talks.
So I would love to come back and see the recording on the YouTube. I think it is available on the YouTube, right?
Probably I'm not aware.
Yes.
Yes. Okay.
Yes,
Yeah.
yes.
There's
Yeah.
yes, Ramesh.
Okay.
Yeah. So
Yeah. So Ramesh, can you send me the link? I mean, that would be nice.
Sure.
Yeah. Thank you.
thank you.
Thank you.
Thank you, Professor Krishnantu, and for your talk, and also thank Professor Abramayan for chairing the session. So now we have our next invited talk, Professor Atul Dixit, IIT, Gandhinagar. I request Professor Sarang Sawhney to introduce the speaker and the audience and chair the session. Make Sani as co-host. He is not able to unmute maybe.
Thank you, Ramesh, for the invitation to be the host for this session. So I'm very happy to introduce to you today Professor Atul Dixit. Am I audible? First,
Also Atul.
Yes. Am I audible too?
yeah, I can hear you. Yeah. Okay. So it's a pleasure to introduce Professor Atul Abhay Dixit from IIT Gandhinagar for today's program. So Professor Dixit finished his computer engineering from the University of Mumbai, and then his MS in mathematics from the Texas Tech University, and his PhD from the University of Illinois at Urbana-Champaign, where his advisor was Professor Bruce Berndt. Now, some of you may know that Professor Bruce Berndt is a very well-known authority on the life and work of Ramanujan, along with Professor George Andrews, and the Lost Notebook, for example, he's one of the authors of that. So Professor Dixit has a very strong connection with Ramanujan, in whose honor we are having this function today. Professor Dixit broadly works in analytic number theory, special functions, and the theory of partitions, modular forms, and Q series. Many of these are, or maybe all of them, are topics which Ramanujan also touched upon, or well, did much more on. And in keeping with his genealogy of finding lost things, new mathematics in lost things, today's talk is on Koshliakov zeta functions and modular relations. Thank you, Professor Dixit. Please go ahead.
Yeah. Thank you, Professor Sani. I think we met in Stanford in 2012.
That's right. Yeah, almost 10 years ago. Right.
Yeah, right. Professor Apurva Kare had organized that research.
Yes. It's good to hear you again. Yeah.
Yeah. Thanks. Yeah. So I'll share my screen.
Please go ahead. Yes.
Yeah. Can you see the screen?
Yes, I can see the screen.
Okay. Good. Maybe I'll do it full screen. Okay.
This is better. Yeah, thank you.
Yeah, this is better.
Yeah, this is fine.
Okay, thanks. Yeah. So good evening, good afternoon, everyone. I would like to thank the organizers, in particular Professor Kashalingam and Professor Sani, for inviting me to give a talk at this conference. I'll be talking on a joint work with my PhD student Rajat Gupta, and this is on Koshliakov zeta functions and modular relations. So let me give an overview of my talk. So I will be first telling you a personal story regarding how I came up with this manuscript of Koshliakov, and then describe the origin and contents of the manuscript, then the theory that Koshliakov has developed in his manuscript, and then the new results that we have further built upon in this theory. So today is the birth date of a mathematical genius from India, Srinivas Ramanujan. So it is apt to start with something related to him. So everybody knows about Lost Notebook of Ramanujan, and its discovery is compared with the discovery of the 10th Symphony of Beethoven. So it's really a marvelous thing. What is Lost Notebook? The Lost Notebook is a 138-page sheaf, so consisting of loose papers, in which Ramanujan wrote in his own handwriting the results that he found in the last year of his life. So that was hidden from mathematical public from almost 1920 to 1976, which is when Professor George Andrews, another authority apart from Professor Bruce Bund on Ramanujan's work, he found it in the Trinity College Library in Cambridge. So for about 56 years, it was hidden from mathematical public. And one doesn't need to say about what impact Lost Notebook has on the mathematical community. It has led to incredibly many advances, not only in number theory and analysis, but also in other areas of mathematics, and more so also in physics. For example, mock theta functions, which is one of the main things in the Lost Notebook, they are applied in string theory, in black holes, and whatnot. So recently there has been like an explosion of work related to mock theta functions in not just mathematics, but in other areas of science as well. And what I'm going to talk about is the discovery of a manuscript, which is, and that discovery, even though is not as charming as that of the Lost Notebook, for me personally, it's really very special that I was fortunate enough to be a part of it. So let me first say that it was not a lost thing, or it was not something which was not published. I mean, this Koshlikov manuscript, but it was hidden from the mathematical public in spite of being published. So let me share some personal story with you before I go to the mathematical contents. So it was during the 4th year of my PhD at University of Illinois that I came across a survey article written by some Russian authors on a Russian mathematician about whom I knew from before, but because I had worked on some of his related stuff, but I did not have any idea beyond what I had looked upon as to what this guy had accomplished. And it turns out that it's very unfortunate that Koshlikov, who made seminal contributions in not just number theory, but partial differential equations and ordinary differential equations as well, his work is now neglected to a large extent. But he turns out to be one of the very outstanding mathematicians from Russia during that time. And the stuff that I'm going to talk about, that is also going to bear testimony to this thing, that he was an outstanding mathematician. So here's a photograph of Nikolai Sergeyevich Koshlikov. Koshlikov is teaching a class. He's talking about the heat equation, as you may see here. As I said, he had done seminal contributions, not just in number theory, but in differential equations as well. So I came across a survey article on his birth centenary that was written by some authors. And why I was interested in that article was because it contained overview of the stuff which seemed to be related to what I was doing in my PhD thesis. And so I was happy and at the same time disappointed, or anxious rather, to see whether there is something that he has already done and which I was working in my PhD thesis. So I decided to really hunt all of his papers. Hunt may not be a good word, but really to go about and find all of his written works to see whether there was any stuff that I'm doing which he has already done. It was a difficult task because most of his papers were in Russian, some of them in German, very few in English. And so to track down those papers, even though University of Illinois Math Library is really very, very well equipped with all of the old journals as well, and from every part of the world, it was a difficult task because sometimes I had to really take help of my Russian friends to even see what type of journal I should be looking for, because the explanation, the bibliographic reference was also in Russian. Nevertheless, I was able to find most of his papers, And I found out that there was no overlap between what I was doing and what he had done. So I was very happy. But at the same time, I came across a very interesting piece of information. And that was that there was a manuscript in that review article. There was a manuscript about which there was connections with the work of Ramanujan. And that was something which really glued me to the survey article and to finding the manuscript. So let me go over one quote in here, which is very inspiring and motivating for teachers and students alike. So it says, the repression of 30s, which affected scholars in Leningrad, continued even after the outbreak of Second World War. In the winter of 1942, at the height of blockade of Leningrad, Koshlyakov, along with a group of scientists, was arrested on fabricated dossier. So fabricated is false dossier, and condemned to 10 years of correctional hard labor. After the verdict, he was exiled to one of the camps in the Urals. Urals are mountains in Russia. On the grounds of complete exhaustion and complicated pellagra, Koshlyakov was classified in the camp as an invalid and was not sent to do any of the usual jobs, the laborious jobs. He had a very serious shortage of paper, and he was forced to carry out calculations on a piece of plywood, periodically scraping off what he had written with a piece of glass. Nevertheless, between 1943 and 44, Koshlyakov wrote two long memoirs. One of them is a study of some questions in the analytic theory of rational and quadratic fields. And the second one is a study of a class of transcendental functions defined by the generalized Riemann equation. So what I would like to really focus upon is this sentence. Many times we see complaining about some minor things like, okay, I'm not able to work because the AC is not working, it's so hot, or I don't have mood to work because somebody said something and I'm now disappointed, or some sort of things like that. We should really take motivation from Koshlyakov whenever we feel such a thing, because you see, he was in the jail, he did not have paper, and yet it did not deter him from working on mathematics. He worked mathematics on plywood, scraped it from a piece of glass, preserved those things, and was able to write these two manuscripts. The object of today's talk is this particular manuscript, which is over 150 pages long. And this one, unfortunately, met an unfortunate fate that it was lost when it was communicated to the mathematical community by the jail authorities. But we are certain that Koshlyakov again thought about the research that he had done in that manuscript, and he, after coming from jail, see, this one got published in 1954. Koshlyakov was released sometime around 1950 or so, and he went back and rethought about what he had done then. I cannot be exactly sure about this, but the title of this and the title of what is written here, analytic theory of rational and quadratic fields, here analytic theory of rational and quadratic fields, that suggests that it was the same one. But the other one was fortunately preserved, and that is the subject of our talk today, a study of a class of transcendental functions defined by the generalized Riemann equation. Whenever Koshlyakov submitted this manuscript, he told the jailer that, please send this to the mathematical community. It is important for science. So these words themselves are very inspiring. And whenever it reached Steklov Institute of Mathematics in Russia, the three famous mathematicians, I.M. Vinogradov, very famous number theorist, Sergei Bernstein, and Yuri Linik, another important person in number theory, they were so impressed by the contents that they immediately recommended its publication. So the next big task for me was to obtain a copy of this manuscript. And it was relatively simpler because the UIUC math librarian, Tim Cole, told me that the Center for Research Libraries in Chicago has a copy of it. And the Center for Research Libraries was so kind enough to scan this whole manuscript, 150 pages long, and send it to me by email. So here is the title page of the manuscript. If you look at this name of the author, it doesn't say N.S. Koshlyakov. First of all, it is in Russian, But even so, it doesn't say N.S. Koshlikov, it says N.S. Sergeyev, whereas Koshlikov's name was Nikolai Sergeyevich Koshlikov. So he decided to author it by means of patronymic name through his father, like Sergeyevich, and here it says Sergeyev. The probable reason could be that if later on mathematical community, and not just mathematical community, but other people also find out that they had jailed this particular person who was such a great mathematician, they might be in problems. So perhaps they wanted to hide his name, and that's why it was written here. As you can see here, it says it was published by Stekelov Institute of Mathematics in Moscow in 1949. So even though the manuscript itself got published in 1949, the churning of the concepts in the manuscript seems to be going on in the head of Koshlikov right from 1930s. So why do I say that? In 1923, Koshlikov wrote a paper in Math Annalen, which has the genesis of what is there in the manuscript, even though manuscript has most of the new content. But the problem through which Koshlikov is led to all of this theory, that was considered by him in this paper in 1923. Yeah, just a moment. I think there is some disturbance, so let me just tell them. I think, is it cause? Are you able to hear a disturbance?
It's okay. I don't hear any disturbance.
Oh, okay, great, great. So,
yeah.
Okay, so as I said, the genesis of this manuscript is a problem in physics, which comes from heat conduction. So let me describe this briefly. So Koshlikov says that if you consider a sphere of radius R2, of which the radiation occurs on its surface into a medium at 0 temperature. So at T equal to 0, the temperature is 0. Okay. Now we place heaters inside the sphere on a spherical surface of radius R1 with R1 less than R2, and suppose the rate per unit time of heat propagation from the whole surface is Q, and then the problem is concerned with finding the temperature of the sphere for positive time T, for any T greater than 0. So people who have worked in heat conduction may immediately recognize that the setup leads to partial differential equation. In Koshlikov's setup, it's again this heat equation, but now you have to have all these physical entities to also be taken care of. So K is thermal conductivity, H is the emissivity of the surface, the specific heat is C, rho is the density of the material forming the sphere, and then the relevant form of heat equation turns out to be this. Now, if you solve the if you try to find the characteristic equation by means of separation of variables, method of separation of variables, then the characteristic equation turns out to be this, where this P is in terms of the R2, the radius of the bigger sphere, H is in terms of thermal conductivity and emissivity, mu is the eigenvalue. It is this characteristic equation that forms the crux of Koshlikov's theory of transcendental functions, which are defined by generalization of the functional equation of the Riemann zeta function. So let me go over the next slide on brief introduction to the theory of Riemann zeta function. Most of the people in here may be knowing about it, but just in case not, then here is the slide which has the important contents. So for real part of s greater than 1, the Riemann zeta function is denoted by or defined by summation 1 upon n to the power s, n going from 1 to infinity. This is an absolutely convergent series for real s greater than 1. But one cannot use it for other values of s. So one has to analytically continue this zeta function, and Riemann himself showed that it can be analytically continued to the entire complex plane except for a simple pole at s is equal to 1. Riemann himself obtained a beautiful functional equation relating zeta of s with zeta of 1 minus s. Why is it beautiful? Because if you consider the left-hand side and change s by 1 minus s, that's what you have on the right-hand side, and yet it is equal. So beautiful symmetry that you see. And you can also write it in an asymmetric form, which takes this form. Let us look at a characterization of the Riemann zeta function due to Hamburger. So Hamburger showed characterization by means of its functional equation. So what did he consider? He considered two Dirichlet series. What do I mean by Dirichlet series? Dirichlet series are things that look like this. So it is summation n equal to 1 to infinity a of n over n to the power x. For S lying in some half plane, so in the right half plane in particular, so it could be real part of S greater than some alpha, where alpha could be a very large positive real number. But still, every Dirichlet series has a half plane of convergence. This is similar to what we have for power series, right? In power series, we look for the disk of convergence. We have radius of convergence, and inside the circle of convergence, we have the power series converging absolutely. Outside, you have a divergent. Similar thing here, you have corresponding to radius of convergence what is known as abscissa of absolute convergence. And if this particular Dirichlet series converges for real part of S greater than alpha, then that alpha is called as the abscissa of absolute convergence. And then if you are to the right half plane, so real part of S greater than alpha, then this series converges absolutely. And then if you are to the left half plane, then it does not converge. On the abscissa of convergence, it is kind of delicate, similar to how for power series on the circle of convergence, it is quite delicate. Okay. So Hamburger considered two Dirichlet series of this kind, f of s and g of s, associated with arithmetic functions. So the defining series of the Dirichlet series has to have the top thing independent of s. Okay. So he considered two Dirichlet series which are absolutely convergent for some real part of s. And if f is a meromorphic function of finite order with finitely many folds, which satisfies this functional equation. So on one side you have f, on the other side you have g, and they are, I mean, this is reminiscent of Riemann's functional equation for the zeta function, right? Because there you have zeta of s here, you have zeta of 1 minus s. If f and g are satisfying this hypothesis, then what does Hamburger's theorem tell us? It says that f and g have to be some constant times Riemann zeta function. So there is really no flexibility. One has to have zeta function back. So this is somewhat similar to Bohr-Muller theorem in the theory of gamma function, if people have seen that. You have three restrictions on the f. It's satisfying some functional equation f of x plus 1 equal to f of x. Then f should be logarithmically convex, and then f should be increasing function. If that is the case, and this is for f's from 0, infinity to 0, infinity. If that is the case, then f has no choice but to be a gamma function. It is similar to that that Hamburger proved for the Riemann zeta function. But later on, he wrote a series of papers. So first of all, let's look at a picture of Hamburger. This is the best that I could find on internet. Later, he wrote a series of papers where he studied the analytic properties of functions which are defined by, again, the generalized functional equation of Riemann, but a symmetric form of it. So in the Riemann zeta function case, here you have zeta 1 minus s, and again you have zeta of s. This factor being exactly the same. But now he considers f and g, and then he has one more flexibility. He's saying that, okay, f can be a Dirichlet series, but g need not be. Then what are the analytic properties? So that's what he worked on, but he did not give any explicit example of this pair, f comma g. That's where Koshlikov's work comes and is very important, because Koshlikov was the first person to explicitly give such a pair. Now, if people are familiar with Hurwitz zeta function, then Hurwitz zeta function is defined by this. Sorry, I forgot to say zeta of s comma a. For real part of s greater than 1, zeta of s comma a is given by this series. Again, this is an absolutely convergent series. And if you put a is equal to 1, here a is between 0 and 1, but a can be equal to 1. So if you put a equal to 1, then this turns out to be zeta of s, the Riemann zeta function. Okay, Hurwitz zeta function satisfies this important formula called as Hurwitz formula, where if you have real part of s greater than 1, but now you are looking at 1 minus s, so that the argument of 1 minus s will have its real part less than 0. Then it is connected back to Dirichlet series for cosine and sine in this particular way. See, this particular factor is exactly what occurred in the previous consideration by Hamburger. See, 2 cosine pi s by 2 gamma of s over 2 pi to the power s. That's exactly what you have here. So when I was working with my PhD student, Rajat Gupta, we were thinking like, why did he not consider, why did Koshlikov say that his example is the first example of such a pair, f comma g? Why don't we have something for Hurwitz's formula? I mean, the Hurwitz zeta function. Does it not have something similar? But note that this form is valid only for real part of s greater than 1, whereas we want something working for all complex values of s. So what Koshlikov did it was for all complex values of s. So let us actually look at his examples of f and g. His f is zeta sub p of s, his g is eta sub p of s. So how are they defined? They are defined by means of series. So this one has a factor in front of it, depending on p, but then you have 1 over lambda j to the power s, which is reminiscent of what we have in the case of Riemann zeta function. But there we have only j to the power s. Now here you have lambda sub j. So I should explain to you what these lambda j's are. And there comes that characteristic equation again. The lambda j's are positive real roots of the characteristic equation. Up to a simple substitution, trivial substitution, this characteristic equation is exactly the same as in that setup coming from problem in heat conduction that I discussed before. Note that P is greater than 0. So he is looking at this transcendental equation and its positive real roots, and with the help of those positive real roots, he is finding this particular series. And the other series is coming from the functional equation. So if f is this, what does g turn out to be? So then he says that, okay, g has to turn out to be this based on the functional equation. And what is this? You have a certain thing in the numerator, but now note that this is not a Dirichlet series because the top one has dependence on the complex number s. Nevertheless, it is a series which converges absolutely for real part of s greater than 1, as is this particular one. Okay. And what is defined by s of 2 pi p k sub k, or if you replace this 2 pi p by more general number nu, then it is defined by means of this integral. Okay, so now why is this theory important? So when you let p tend to infinity, note that p is any positive real number. So if you let p tend to infinity, what is going to happen? Let us look here. This factor, if you divide numerator and denominator by p square, then it approaches 1. What happens here is that lambda j's approach j, and hence you have 1 upon j to the power s. So summation j equal to 1 to infinity 1 upon j to the power s is nothing but Riemann zeta function. But why is it that lambda j approach j? So observe this equation, write it in the form tan pi alpha is minus lambda over p. Okay. If you let p tend to infinity, the right hand side is 0. So you have tan pi lambda is equal to 0, which implies that sine pi lambda is equal to 0. And so what should lambda be? All these lambda j's should be nothing but j itself. So that implies that when p tends to infinity, lambda j's approach j. Now what happens when you let p tend to 0, the other end? So tan pi lambda is minus lambda over p. P tends to 0. So tan pi lambda is equal to minus infinity. So from there, you will see that one has to look for the roots of cosine, the denominator. Cos pi lambda is equal to 0. And those are at j minus half. So when we let p tends to 0, lambda j's approach j minus half. And what do we get in that case? As I said, in p tends to infinity case, lambda j's approach j. So you get nothing but zeta sub p of s approaching the Riemann zeta function. And then eta sub p of s approaches as p tends to infinity, again Riemann zeta function. So here, if I go with the second one and I let p tend to infinity, what am I going to see? See, nu is 2 pi p. So I put here 2 pi p. And so you divide the numerator and denominator again by 2 pi pk. And when you let p tends to infinity, that will simply give you 1. So then 0 to infinity e raised to minus x, x to the s minus 1 dx is nothing but gamma of s. So you have gamma of s over gamma of s. So it turns out to be 1 upon k to the power s, which is nothing but the Riemann zeta function again. So when p tends to infinity, both give you the Riemann zeta function. When p tends to 0, then they give me this two things associated with the Riemann zeta function. So why is it important to study these two functions, which we have called as Koshlyakov zeta functions? The important thing is that in special case, when p tends to infinity or p tends to 0, these are giving me Riemann zeta function. And so the whole theory of the Riemann zeta function is coming as a special case, provided we develop all of the results in the Riemann zeta function to the Koshlyakov setting of Koshlyakov zeta functions. Anyway, what Koshlyakov showed, and let me go over it briefly. So Koshlyakov showed that both zeta sub p of s and eta sub p of s can be analytically continued to the entire complex plane except for a simple pole at s is equal to 1 for each of them. The zeta sub p of s having the residue 1 at that pole s equal to 1, and eta sub p of s having the residue 1 over 1 plus 1 over pi p at s is equal to 1. Okay, as p tends to infinity again, this becomes 1, and this is tending to zeta of s. So you can see familiar thing that the residue at s is equal to 1 for zeta of s is nothing but 1 itself. Okay, as I said, they satisfy this functional equation. So the study for this functional equation with f and g itself led to this zeta sub p and eta sub p. Now let me go with some brief overview as to what all is there in this manuscript of Koshlyakov. There are really a lot of things. It's a 150-page manuscript, but I'm only concerned today with the stuff that we will be requiring for our new results. So he constructed the whole theory of zeta functions based on these fundamental ideas that he had, and also not just that, of functions which are related to the zeta functions. So for example, in one instrumental thing for the theory of Riemann zeta function is gamma function. So here he has generalized gamma functions, which he calls as gamma morphic functions. There are 2 of them. He has generalized Euler constants, 2 of them. Generalized Bernoulli numbers or Bernoulli polynomials as well. Generalized theta function, Jacobian theta function. Generalized Hurwitz zeta function, etc. So one question that people may have is that, okay, in the case of zeta function, we have only one gamma function. Why are there 2? In the case of zeta function, again, there is only one Euler constant, gamma. Why are there 2? Because there are 2 zeta functions. So corresponding to each of them, you have one gamma function each, one Euler constant each, the generalized Euler constant. Okay. So manuscript also contains a full chapter on summation formulas, which generalize known summation formulas due to Poisson as well as Abel-Plana. So let us look at Lorentz series expansion of zeta sub p of s. We know that it has a pole at s is equal to 1. So it has to have a singular part, which is 1 upon s minus 1 in the case of zeta sub p of s. The constant term is nothing but the generalized Euler constant Cp1. And then you have positive powers of s minus 1. Okay, what is the generalized Euler constant? It's defined in this way. Again, if you let p tend to infinity, you will see that this gives you the familiar Euler constant. Eta sub p also has a simple pole at s is equal to 1, but the residue is this. So you have this as the singular part. And now the constant term is somewhat complicated. It not only consists of this Cp2, which is defined in this way, but it also consists of what is known as the incomplete gamma function here. Okay. He obtains analogs of the results in the theory of gamma function. For example, the Weierstrass product expression representation for gamma, that is generalized to these 2 gamma morphic functions. So for gamma 1 comma p, he has this. So if you look at how it looks in the case of gamma of s, then it has e to the minus gamma x, the small gamma, e to the minus gamma of x over x times this such a product. And in this case, instead of that gamma, we have Cp1, the generalized Euler constant. So when p tends to infinity, as I said, we get back the familiar functions. He also looks at the logarithmic derivative of gamma 1 comma p, the psi function or digamma function that we call. So generalized digamma function, he has a series representation for it. He also gave another representation which is crucial in our work. It's in terms of this function sigma of t. What is sigma of t? Even though it looks like it is independent of p, it is actually having dependence on p. It's just p plus t over p minus t. We have retained the notations of Koshlyakov as it is in our work. Again, let me go quickly over this. There is a Weierstrass product expression for the other gamma morphic function. There is other generalized digamma function, and there is another representation for this generalized digamma function in terms of an integral, which looks like this. But now you have sigma sub p of t. What is that function? It is nothing but this particular series. Okay, so with this, if you come back to the functional equation and ask yourself, okay, this is the asymmetric form of the functional equation. What about the symmetric form? Then Koshlyakov also gave a symmetric form, which is taking the average of the two zeta functions, zeta sub p of s plus eta sub p of s divided by 2. And he calls it as omega sub p of s. And if you define it in this way, then this is the functional equation. It's perfectly symmetric and perfectly reminiscent of that of Riemann, just that instead of omega sub p of s, you have zeta of s. Here, instead of omega sub p of 1 minus s, you have zeta of 1 minus s. And as p tends to infinity, of course, you get back the Riemann zeta function. And also in terms of p tends to 0. Let me also look over what is known as completed Riemann zeta function. So note that Riemann zeta function has a simple polar at s is equal to 1. So in this completed zeta function, what am I doing is I'm multiplying it by s minus 1, so that the pole at s is equal to 1 is killed. Also, when I have s equal to 0, that is going to kill the poles of the pole of gamma function at s is equal to 0 is going to be killed by this s. Okay. Now there are also poles of the gamma function at negative even integers. When you have s over 2 as the argument, you also have poles at negative even integer. But the Riemann zeta function itself has zeros at those negative even integers. So this is an entire function of s. And when you evaluate it on the critical line, real part of s is equal to 1/2, then that is what is called as cap c function or c of t. I'll just go back c of t. Ramanujan has one full published paper on Riemann zeta function in which he obtains very beautiful modular transformations. Why do I say these to be modular transformations? Is because on one side you have stuff involving alpha, on another side you have the same stuff involving beta, or let's say a and b, where b is some constant over a, as is here. And then he also relates it with some functions involving the cap c function of Riemann. So Koshlyakov also devotes the last chapter of his manuscript fully on generalizing results of Ramanujan, and that's where actually I came in contact with this manuscript through that survey article, because I was working on related modular transformations. So Koshlyakov considers a completed Koshlyakov zeta function, the first one, sorry, not the first one, with the average of the two, zeta sub p of s plus eta sub p of s divided by 2, that is the omega of p of s. And he considers the completed such zeta function. And when you evaluate it on a real part of s is equal to half, that is what he calls as xi sub p of t. And now, this xi of t is actually even function of t. It just comes trivially through the functional equation. Similarly, xi sub p of t is also even for even values of t as well as real for real values of p and t. And Koshlyakov actually generalizes Ramanujan's result that I showed on the previous slide. Okay, where do you have dependence on p on the integral on the far right? It's here in the definition of this xi sub p of t. That's where you have the p. Okay, now again, today being a National Mathematics Day, let me come back to something done by Ramanujan in his last notebook, a beautiful result on page 220, involving the psi function, the logarithmic derivative of gamma function. Ramanujan defines this function phi of x as psi of x plus 1 by 2x minus log x. These two expressions are reminiscent of something. What is it reminiscent of? So if you look at asymptotic expansion of psi of x as x tends to infinity, the first term in its asymptotic expansion is minus 1 by 2x. Here you see plus 1 by 2x. The second term is log x. Here you see minus log of x. And then you have terms involving 1 by x squared, 1 by x cubed, 1 by x3, 1 by x to the power 4, and so on. So if you subtract off the first two terms in the asymptotic expansion of psi of x from itself, then you'll get this function phi. And then what will it be equal to? That will be nothing but big O of 1 by x squared. When you have big O of 1 by x squared for this phi, then you can actually build an infinite series, because this will be big O of 1 by n squared, and so this is absolutely convergent series. So that's what Ramanujan does. He adds some residual terms to it, multiplies the whole thing by root alpha, and then observes the beautiful symmetry. See, alpha and beta are two positive numbers such that alpha times beta is equal to 1. And what is he saying? This expression is unchanged when you replace alpha by beta. And not only that, this is also equal to this particular integral involving the Riemann-C function. Now, transformations of these kinds are really very important in the theory of modular forms. And exactly this is an example of a modular transformation corresponding to the inversion. So if you look at, for example, modular forms on SL2Z of weight K, what do you have as one of its properties, defining properties? That f of minus 1 by z is z to the power k f of z, where k is the weight of the modular form. So that z going into minus 1 by z, that sort of thing is called as inversion, right? Where z is in the upper half plane. Now, instead of considering z in the upper half plane, we are considering alpha in the right half plane. I mean, this can be easily extended to alpha and beta such that real part of alpha is greater than 0, real part of beta is greater than 0. And so that z going into minus 1 by z, that inversion, that translates in here to alpha going into 1 by alpha or alpha going into beta. And we are saying here that alpha goes to beta leaves this transformation, leaves this expression unchanged. So you get a modular relation. Now, I should tell you one personal story which really is, I mean, I was very fortunate that I was part of it, because this is something that I worked on my PhD thesis. I started my PhD thesis with this, and then I have some other generalizations, analogs, and many other things. So it so happened that in my second summer, when I was doing my PhD, summer of 2008, there was a lecture by Professor Bruce Byrne titled Unsolved Problems in Ramanujan's Lost Notebook. And I had read that email, but somehow I forgot about it. And I was going to my office, which was next across the road in the next building. And I met another student of Professor Bruce Byrne, who was also doing his PhD. And he told me, "Aren't you coming to the lecture?" I said, "Which lecture?" He said, "Oh, he's giving." That's when I came to know that, okay, there is this lecture. So I immediately ran to attend that lecture. And this problem was given as one of the unsolved problems at that time. And when I looked at this problem, many of you may have experienced this feeling, right? That whenever you look at something, you're hooked to it so much that you think of nothing else. So I decided on that day to myself that I should stop whatever I'm doing right now. I did not have any thesis problem at that time, but I was working on some stuff that I liked. And I realized that, okay, I should stop everything that I'm doing and just concentrate on solving this problem. Part of the reason was not only because this was unsolved, the other thing was that I really loved, and I still do love, gamma functions. And so I worked on it for about 2 weeks, and then I was able to solve this, and I was very happy. I still did not know at that time that this would lead me to the main topic of my PhD thesis. But I showed this to Professor Bruce Byrne. He was really very happy. And he told me one very nice thing. I had shown that, okay, this integral is equal to this, and then this integral is also equal to this. He told me, you don't have to show it twice. Just prove this is equal to this that you have shown. Then replace in there alpha by beta. So here you will get everything with beta. Here you will put beta. What is beta? 1 by alpha. Log of 1 by alpha is minus log alpha. And cosine of t by 2 log alpha or cosine of minus t by 2 log alpha is the same. So you get back this integral. So this invariance is explained by means of this integral. The integral remains invariant as you replace alpha by beta. So this is what he said. I mean, this identity comes for free. So you just have to prove this one. And then we simplified my proof also, and then we wrote a paper together. So at that time, I really liked this idea of proving modular transformations using these integrals of Riemann zeta function. So that's how I got my main topic of PhD thesis, one of the two topics. And I just thought I should tell you this story. But then when we looked at Koshlikov's work and the last chapter of his manuscript generalizing the work of Ramanujan's published paper, we decided that, okay, let us try to generalize this in the P setting. So Rajat and I then worked on it, and we did get this. Why is it nice? Because now, when you do it for the P setting, you get an infinite family of formulas. For every real valued P, you have such a result. And when you let P tend to infinity there, you will get Ramanujan's result as a special case. So let me give you the hypothesis of the main theorem. So the capital phi sub P of x is sum of these two phi functions, where each of them is defined in this way. Now, if you look at what was in the Ramanujan's case, it's exactly analogous to that. The psi function gets replaced by psi 1 comma P of x. And also you have two gamma functions, right? So you'll have two such digamma functions. And then we do the same thing. We remove the first two terms from their asymptotic expansion as x tends to infinity. And then we form these two functions and we add them, and that is phi sub P of x. Recall that I defined earlier these two generalized Euler constants. Okay. They are also given in Koshlikov's manuscript in terms of these integrals, but we require one new integral representation which was not given in Koshlikov's work, and that is this one, for the CP2. Okay, and this is our result. So this paper got published in Advances in Mathematics in last month, or I think last to last month, but it is going to, I mean, I think the page numbers are going to be announced just 2 days from now, on 24th of December. So with the above hypothesis and with the understanding that alpha and beta are two positive numbers such that alpha times beta is equal to 1, you have this beautiful symmetry, which is also reminiscent of the symmetry in Ramanujan's case, right? There was only one gamma, but now we have to have two generalized Euler constants. Then you had log 2 by alpha over 2 alpha. You have the same thing, but in front you have this factor. And then whatever you have here in alpha, you have the same thing in beta. And now you have this integral where the only place where you have P is here. And now I should actually tell you why it was difficult in our case to conceive such a result. Because if you look at Koshlikov's generalization, this one, of Ramanujan's result, there was only one Xi function. So Koshlikov put Xi sub P of T by 2. Here he put a T. With this one, he worked. In our case, if you look in Ramanujan's result, you have C of T by 2 square. I mean, C of T by 2 is a real function of T, so one can actually take it up outside of the absolute value sign. So really, you have square of C sub T of 2, T over 2. And what will you do? Naturally, you'll attach your P again for each of them, right? That's what we started with. And then we were really stuck. Why were we stuck? Because when you go with the squares, you are going to have to look for analog of zeta square of s. And zeta square of s has Dirichlet series representation summation d of n over n to the s, where d of n is the number of devices of n. And something like that we don't have in the setup of Koshlikov. Okay. So we decided that, okay, how to then even look for such a formula. We decided to generalize this left-hand side. And then with the help of that, move on to what we get here. And then we found out that if you do that, then it's not for each of these functions that you have to attach this P, but only for one of them. And that we would have never thought of if we had not approached from the other side, other equivalent expression for it. Anyway, as I said, if you let P tends to infinity, you get back Ramanujan's result. Let me skip the proof because how much time do I have, Professor Kashilingam?
Actually, it's still 1, I think.
Okay. Yeah, I started somewhat late. That's why I
Yeah,
was asking.
maybe. Yeah, sure. We can.
So maybe I'll take
we can
10
move
minutes.
on. Yeah, sure.
Okay. Okay. Thank you. So let me skip this proof on account of less time, but let me tell you that what happens when we get P tends to 0, we get a new formula. So this is the new formula. If you look at the form of this, again, it is very reminiscent to Ramanujan's form. The only change being that here you do not have 2 pi alpha, just pi alpha on both sides. But what is this function? That now consists of 3 gamma functions, 3 digamma functions. Okay, so that's a new thing. And the integral here on the right also changes. It has this factor attached to it. How do we get it? From our general P result, when you look at P tends to 0, as I said before, lambda j is 10 to j minus half. So from there, one has to really work on. It takes time, but one can actually prove it. And it's very explicit. Now let us move to second part of our talk, which is also associated with another formula of Ramanujan. So Ramanujan gave this beautiful formula linking odd values of the Riemann zeta function, or in other words, I should say really Riemann zeta function evaluated at odd positive integers or odd negative integers. Okay, zeta to m plus 1. These are really difficult ones because there is nothing known about the arithmetic nature of zeta to m plus 1 except for zeta of 3. Roger Aperi, he showed that zeta of 3 is irrational. But we still don't even know whether zeta of 3 is transcendental. See, transcendence will imply irrationality, but not the other way around. So we only know that zeta of 3 is irrational. We don't even know that for other values, zeta of 5, zeta of 7, zeta of 9, zeta of 11, and so on. We don't know whether these are irrational numbers. Forget about transcendental. We don't even know whether they are irrational numbers or rational numbers. Nothing is known. It is believed that all of these values are transcendental, but one doesn't have any proof up to now. Zeta of 1, of course, is undefined, right? We have a pole. So the best result up to now for these higher odd zeta values is that of Vadim Zudilin, which tells us that at least one of the 4 values, zeta of 5, zeta of 7, zeta of 9, or zeta of 11, must be irrational. But we don't know as of now how to narrow it down to one of these 4 ones. So Ramanujan's result is special in that regard, that one has from here a beautiful almost modular relation. I say almost modular relation because here you have something which has only alpha, and you have exactly the same thing having beta, where alpha beta is pi square, up to the effect that you have this minus 1 to the power minus m, or minus 1 to the power m. But that modularity is obstructed by means of this finite sum involving the Bernoulli numbers. Okay, so that's the obstruction to modularity. Why is this formula important? It really encodes many important things about modular forms on SL to Z. If you take your m, see, this is true for any non-zero integer m. So if you take your m to be negative integer, let's say minus 3, minus 2 onwards. First of all, let us take negative integer less than minus 1. If you take, for example, minus 2, then you get 4 minus 3, that is 3. So j cube over 2 alpha j minus 1. This is going to give you the transformation formula for E4 of Z. The Eisenstein series of weight 4 on SL to Z is E4. That transformation formula is what is being intended by Ramanujan. And see here, now the obstruction to modularity is gone because you are putting m is equal to minus 2. So you have a sum going from 0 to minus 1. So that's an empty sum. So you get a perfect modularity, and that's the modular transformation for E4 of Z, the Eisenstein series of weight 4. If you put m to be minus 3, then you get for E6 If you do it for -4 and so on, you get for E8, E10, and so on. You might be, people in modular forms, of course, know that E4 and E6 generate the vector space of modular forms on SL2Z, right? So in that regard, this is very useful. What happens when you put m equal to -1? This gives me j to the power 1. And that is nothing but the transformation formula for the quasi-modular form E2 of Z. In Ramanujan's notations, E2 is P, E4 is Q, and E6 is R. And note that why do I say quasi-modular form? Because when you put m is equal to -1, this term, this is having one term, it's not vanishing. J going from 0 to 0. So that has obstruction to modularity, because of which you don't have it as a modular form, but it is a quasi-modular form. But now, when you put here m equal to positive natural number, or no need to say positive natural number, just natural number, say m equal to 1, 2, 3, and so on, then you get transformation formulas for what are known as Eichler integrals of Eisenstein series of SL2Z. So that is also encoded in here. The remaining thing is m equal to 0. Of course, the formula doesn't hold because at m equal to 0, this becomes zeta of 1, so it has a pole. But the series perfectly makes sense. It has exponential decay. And if you start with that series, then you will end up with transformation formula for Dedekind eta function, which is a half integral weight modular form. And that is also encoded in here. So this formula is really very, very important. And so we decided that, okay, how do we generalize this to the P setting? So that is what I will just tell you. So this is the formula that we had. And here the Bernoulli numbers get generalized to Bernoulli polynomials, which are, generalized Bernoulli numbers of Koshlyakov, which are defined by means of this integral. The sigma sub P of x is a function I already denoted previously, but it is defined again in here. So this involves zeta sub P of s. I mean, odd values of zeta sub P of s. So let me skip some of the stuff because I'm short of time. But there are many, many special cases of interest that come. For example, many a times we got new results in the theory of Riemann zeta functions by letting P tend to 0. And that is a typical thing. When you let P tend to 0, most of the times you get new results. So to the best of our knowledge, we did not encounter this formula anywhere. So to the best of our knowledge, this is new. New formulas for zeta at 4m plus 3. So zeta 3, zeta 7, zeta 11, and so on. Okay, so let me conclude by saying that we have merely scratched the tip of the iceberg of Koshlyakov theory, because this theory was dormant, lay dormant for almost 60 to 70 years, hidden from the mathematical community, not because it was not published, it was published, yet it was hidden in some way, unfortunately. Only mention of this manuscript is in a PhD thesis of one Russian mathematician called Alexander Kesunko, but that too is just one sentence that, okay, Koshlyakov worked on some generalized zeta. That's it. No new property, no study of Koshlyakov's work. And so I think this is very important in particular for people working not only in number theory, but also for physics, because the problem comes from physics. This leads us to a new generalized zeta function theory, which might be as important as the applications that one are seeing of the zeta function theory in many areas of science. There are still many fundamental questions which are left unanswered. So let me begin the fundamental unanswered questions even in Koshlyakov's theory. Forget about the stuff that we have done and things that are leading from there to some unanswered questions. So let us start with the zeros of Koshlyakov zeta function. Koshlyakov showed that for every positive real number, the trivial zeros of zeta sub p and eta sub p are at negative even integers, which is the very same thing as in the case of zeta function itself. Koshlyakov generalized Euler's famous result relating zeta of 2k with b2k, and which actually tells us that all even zeta values, all zeta 2, zeta 4, zeta 6, zeta 8 are transcendental because they are rational multiple of pi to the 2k. So Koshlikov has a generalization of that result for zeta sub p. And with the help of that and the functional equation, one can actually evaluate eta sub p straight away at 1 minus 2k. But there is no mention of zeta sub p of 1 minus 2k. Say here it is eta sub p of 1 minus 2k. There is no mention of zeta sub p of 1 minus 2k or also eta sub p of 2k. By means of functional equation, these two are related. Partly this is because of the fact that eta sub p of s is not a Dirichlet series. So it may be interesting to get closed form evaluations of either this or this. If you have one, then the other will be also similar. We were able to obtain Ramanujan's, generalization of Ramanujan's formula for zeta sub p of 2k plus 1, but not for eta sub p of 2k plus 1. So that is another thing that one may try. Non-trivial zeros are not at all addressed in Koshlikov's manuscript. Recently, my student Rajat and I are working on some results related to non-trivial zeros, but we are just in the beginning stages. And combining these two cases, one actually gets this result. The nice thing about it is that if you now put alpha also equal to 2, you have cos square p by 2 log 2. So that is positive. Everything else is positive. The integral is positive, and this leads us for free to these important inequalities. Okay, and with that, I will stop. Thank you.
Yeah, thank you, Professor Dikshit, for a very wonderful talk, including lots of personal anecdotes. So let me see if there are maybe I had a question before I had a comment before I let others ask questions. Now, my comment first was that the historical mention you made about him having a hard time in jail, etc. So I remembered there was another mathematician named Leray who has a somewhat similar history of shifting from differential equations to sort of homological algebra because he did not want the Nazis to put him to.
Oh, what's his name?
Leray, Jean Leray.
John Leray.
Leray. He is J.P. Sayre's advisor.
Oh,
Yeah.
I didn't know that. Thanks for informing. Yeah.
Right. So he's, I mean, he's done many things, but one amongst them is that he invented things called spectral sequences, which of course are now
that's interesting.
predominant in lots of homological applications to geometry and algebra. Anyhow, the other question I had was just so that I understand you right. If you understand what are the zeros of this new zeta function, you have solved the Riemann hypothesis. Is that correct?
No.
No.
Because but so it doesn't imply that way, because even if you look at zeta sub p of s and you try to look at the non-trivial zeros of it, suppose I'm pretty sure that the location of the zeros, non-trivial zeros of that generalized zeta function will depend on this parameter p.
Okay.
And suppose as p tends to infinity, if you are able to show that, okay, that tends to half.
Yes.
So that the real part is half. Then you have solved Riemann hypothesis. But
right.
For up to now, we don't have any information about the non-trivial zeros. But I mean, coming back to your question, one nice thing that this does is that it gives you flexibility to play with one more additional parameter. So if you have really obtained information about how the non-trivial zeros for the zeta sub p of s looks like, and then somehow by taking p tends to infinity, if you are led to half, then I think this will really be very important, like solving the Riemann hypothesis.
Right. Can it happen that you take p tends to infinity and the values that it takes become close to zero, but they are not zero themselves? Like, is that possible? Or?
So right now, we are really in the very beginning stages of knowing about the non-trivial zeros. So Rajat and I are working on, first of all, trying to get an analog of Hardy's result, that there are infinitely many zeros on the critical line. So I think after we have some better idea about where do they lie and then how do they look, at least for some of them, Perhaps then letting p tends to infinity will give us some important information about Riemann zeta zeros.
Thank you. So let me check if there are questions. None on chat. No, none on YouTube either. Okay, so it doesn't look like there are any other questions. So thank you again very much, Professor Dixit, and
Sure.
I'll hand it over back to Ramesh.
Sure. Thank you, Professor Sani.
Thank you.
Thank you, Ramesh.
Thank you, Professor. Thank you, Professor Atul Dixit, for your talk. I also thank Professor Sarang for chairing the session. Thank you very much.
Thank you.
We will now have a short lunch break and join together for our next invited lecture at a sharp at 2 p.m. Thank you. We will meet back at 2 p.m.
Bye.
Thank you very much, Professor.
Thank you.
Now share.
Hello, Promise, can you hear me?
Yes, I can able to hear.
Okay, so it should be okay then.
Soundman, are you able to hear my voice?
Yes, yes. As loud as I can hear from my office.
Okay. Okay.
Hello, Sumik. Thank you. Okay, I cannot hear you. Ramesh?
Yeah, now can you hear me?
Oh, yes. Oh, again some problem.
Yes, I did it. I did.
Okay.
Now you can able to share. Yes.
See my screen. It will screen.
Welcome back. The next section, and I'm welcoming Dr. Savik Basu as well as Sauman Sarkar for chairing the session. Sauman Sarkar, please take care of the session.
Thank you, Ramesh. Yeah, I'm happy to introduce my friend Somik Basu. He did BMAT from ISI Bangalore Center around 2004. Of course, Before that, he represented India in International Mathematical Olympiad in 2000 and 2001 and received silver medal in both that time. After that, after BMath, he did integrated PhD from Harvard University, and under the guidance of Michael John Hopkins. And very soon after his PhD, he was postdoc in University of Copenhagen. Is it the spelling? Or Copenhagen? Okay. And then he wanted to come back to India, and of course he chose our lovely city of joy, that Calcutta, and he joined at Ramakrishna Mission, Vivekananda University, and after that, after a few years, he moved to ISI Kolkata. So today he is going to talk about the structure of unstable homotopy groups. Please, Humik, you.
Okay. I hope everyone can hear me. Am I audible?
Yes, we can hear you.
Okay. Thanks. So first of all, I should thank the organizers and colleagues for inviting me to give this lecture. I should thank Showman for the very kind introduction. Then let me begin. I thank the organizer for doing this program. It's a really nice thing that we remember of the brightest Indian mathematicians, Ramanujan, celebrating a day in his honor. Unfortunately, the area which I work in does not match with Ramanujan used to do research in, but I'll describe some things about. So the area I work in is algebraic topology, or more specifically homotopy theory. I want to tell you some general facts about this area, and also I point out some results which we have proved. The work is joined with David Blank and Devashish Sen. So I'll just talk about some general, I give you some general idea about this area of groups. Maybe many of the terms are not usual in Indian mathematical circles, but I hope that there will be people who will be interested in the coming years. So my lecture is going to be about the structure of unstable homotopy groups, and you will see what are the meaning of these terms. So,
Sorry, Samik,
yes.
Can you loudly speak? Your voice is
Yeah.
very low.
Oh, my voice is low. Maybe the mic
Yes.
is pretty much away from my. Maybe if I speak like this, is this better?
Yes, super.
Okay. Yeah, that's what I thought. Okay, sorry about that. So, in algebraic topology, we are interested in this category, top, which is the category of topological spaces, which means that there is a set of there is a class of objects. Objects are all the topological spaces, and the morphisms are the continuous functions. We are studying the topological spaces and continuous functions. So inside this category, we have all the interesting objects from differential geometry or complex geometry or things like that, we have all the interesting objects like complex varieties, smooth manifolds. But there is another advantage. So why in topology, why do we work with this category top instead of say the category of complex varieties or the category of smooth manifolds directly? Because in when we work over this topological spaces, there is a flexibility that we can make various constructions, and this flexibility allows us to define algebraic invariants. Okay, so for example, so people who are doing algebraic geometry, they would know that it is a very big deal to construct the orbit space with respect to a group action in algebraic geometry. While if you are in topology, there is a very easy construction which you learn in a first course in topology using the quotient space. And given any topological space with a continuous action, you can form the quotient space. So that is the flexibility this category offers us, which makes it really nice. Similarly, smooth manifolds also, there are, it's very, there are only certain things you can do. It is still somewhat flexible, but not as flexible as topological spaces. Okay? So the point here is that in topological spaces, you can make these various constructions, and that allows us to define algebraic invariants. That's the point. And algebraic topology deals with this philosophy of assigning algebraic invariants to topological spaces. Okay. So from the perspective of algebraic invariants, okay, so one thing you have to understand here is that if I have an algebraic invariant, that means I am assigning something like a group or a vector space or something like that, R module, to a topological space in a nice manner. So if I have a function, continuous function between topological spaces, then I should give a morphism, homomorphism between the corresponding algebras. Like if it's a group, then it should be a group homomorphism and so on. So if so the topological category, you see the morphisms, you can, for it has a structure of a topological space. Like you can talk about the space of maps between two topological spaces. So you can so a path in the space of maps, for example, is like a continuous deformation from one continuous function to the other. But the algebraic category is kind of discrete. So whenever you have this kind of continuous deformation, that should goes to something to an equivalent thing in terms of the homomorphism. So if you have if two functions are related by some continuous deformation, they will actually induce the same thing, the algebraic invariant. That is the idea. So the notion which captures this theory of continuous deformation is homotopy. So you define that if you have two continuous functions between x and y, they are said to be homotopic if you have a continuous function from x cross the closed interval 0, 1 to y, in which the value at 0 is the first function and the value of at 1 is the second function. So that's so if you have two homotopic maps, the algebraic invariant is expected to give you the same operation. Okay, so that's why this category here becomes very important. It's called the homotopy category of topological spaces. So objects are topological spaces and morphisms are the homotopy classes of maps. So it is it is important. Yes, reasons. So here Yeah, here I put some star here, this homotopy category. This star refers to the base point. There is a notion of a based topological space, which is basically a topological space together with a base point. Okay, and the universal invariant of a topology of this category, homotopy category of topological spaces, is the homotopy groups. What we would do, you will look at the homotopy class of maps from a k-sphere to your space X. That is called pi k of X, and it is a kth homotopy group assigned to a space A. So pi 0 is just something called a pointed set at k equal to 0. At k equal to 1, it is called the fundamental group. It has a group structure. And k greater than equal to 2, it becomes an abelian group. So the pi 0 is the set of path components of X, becomes a pointed set. Pi 1 is a group called the fundamental group, which you study in the first course in topology. And for k greater than equal to 2, this pi k of X becomes an abelian group. Okay. Now this is like the universal invariant, and the computations of these groups are very difficult in general. So by difficult, I mean very little is known. So if X is the circle S1, then it is known that k equal to, it is path connected, so k equal to 0 is just a single point. K equal to 1 is the integers for S1, and k greater than equal to 2 is 0. S1. But if you start taking, like if you take this 2 sphere, the answer is not known for all values of k. So typically, these groups are very difficult, and it is not expected that the answer will be computed for a given space. So it is not even expected. So unless the space has is very specially constructed, it is not expected that this can be computed. But this is like the biggest is the best collection of invariants which can define which can allow us to give you the structure of the topological space almost. Okay, so the computations of these groups are very difficult in general, and there are very few systematic theorems which tell you about the computations. One of the most famous is this theorem of Serre. It says that this pi k of Sn, of course, pi k of Sn, one thing I should say, if k is less than n, it is known to be 0. K is less than n. And pi n of Sn, this was calculated by Hoff, who showed that pi n of Sn is isomorphic to Z. It's called the Hoff degree theorem. This was computed in the 1920s by Hoff. So Serre, this is in 1950s. It is because this he did, I think, during his PhD, and it was because of this he got the Fields Medal. So this theorem says that pi k of Sn is a finite abelian group, except in two cases. Pi n of Sn, which is Z, this is Hoff's result, and pi 4n minus 1 of S2n, which is the group of integers Z, direct sum a finite abelian group. Okay, so there are exactly two cases in which we have something which is not finite, and even then the not finite part is a copy of the integers. Okay, that is the theorem. So before Serre, it was not even known whether these abelian groups that you were getting were finitely generated. So first, actually, Sayre proved that it is finitely generated. Then he proved the stronger result along the same methods. Okay. If you have any questions, I guess you can just ask. It's very hard for me to see the chat or anything. Looking at the slides. Let me go to the next slide. So one thing is that, yes.
If they ask question, then I will inform you.
Okay. Thank you, Showman. Thank you. So, yeah. So from the previous slide, you see that if I take tensor with the rational numbers, this Q here, although it's a bit, I guess the writing is not very nice. If you take tensor with the rational numbers, all the finite abelian part goes away. So this computation gives a Sayre's computation gives a formula for this pi k Sn tensor Q. So that's the rational homotopy groups of spheres. Okay. Now I will do something nice, and I will tell you one fact which is really important. So you define this H top Q. This is called the rational homotopy category. So what you do is you look at the category of topological spaces, and H top was defined using homotopy classes of maps. It is like it's like inverting things which are homotopy equivalences. This H top Q, what you do is you invert those arrows in the category which are isomorphisms on homotopy groups tensor with the rational numbers. Okay. You may be confused about how to do it, but just assume that there is a construction like that, and you can construct this rational homotopy category of spaces. There is a strict theory about how to do it. So you can look at the rational homotopy category of spaces, and among them, I am looking at actually my concentration is about the simply connected ones. So I'm looking at the rational homotopy category of simply connected spaces. That's what the result I will be talking about is going to be about. So there is a remarkable result. It was proved around the same time by both Quillen and Sullivan. It shows that this rational homotopy category, which I just wrote, this is actually equivalent to an algebraic category. Okay? So what do I mean by algebraic category? Algebraic category is something like the category of chain complexes or the category of vector spaces or something like things like that. Okay? So it was proved around the same time, both Quillen and Sullivan, and they showed that this rational homotopy category here, this is equivalent to an algebraic category. So more specifically, this is what Sullivan showed. Sullivan constructed this H top Q to this arrow he constructed to commutative differential graded algebras, and showed that this if your underlying space is simply connected, this rational homotopy type can be obtained using this commutative differential graded algebras. So there is something. So this one is actually stronger than what I am saying. It's what is called a Quillen equivalence, and Quillen showed that this one is actually equivalent to the category of differential graded Lie algebras. These are two different arrows. Okay? I mean, if you think about it a little bit, if you know a little bit of differential topology, you may be able to guess where this Sullivan's arrow comes from. you know that if you have a manifold, there is something called the DRAM complex of forms, whose cohomology gives you the DRAM cohomology groups. So it is isomorphic to the singular cohomology with real coefficients. Now the DRAM complex is what is an example of commutative differential graded algebra, because there is a multiplication given by the wedge of forms, and there is a differential given by D, and D acts as a derivation. The multiplication is graded commutative, hence the word commutative. It's an example of a commutative differential graded algebra. So what Sullivan did here is that he just constructed one this DRAM complex over the rational numbers, and two, he extended it from manifolds, from smooth manifolds to topological spaces in general, using some special constructors. So this is like constructing a DRAM complex. That's what Sullivan did. And then it was using that, he could show that this is actually an equivalence, homotopy categories. What Quillen did is something which I will state a little bit later. But this Quillen's approach is basically about taking homotopy groups. And then you would ask the question, why does the Lie algebra come in? Lie algebra has this Lie bracket. This Lie bracket comes from an operation on homotopy groups, which I will just talk about. Yeah. So this is thing here. So, yeah. So this says that. So a way of so what do we have to do? We have to understand these homotopy groups. We have to understand how to get these elements in a homotopy group. So we need to know how to construct new homotopy elements. So one way is by performing certain operations on existing homotopy classes. Okay? So what kind of operations? There are some obvious operations. You know, you have the group structure, so you can add and multiply homotopy classes. Of course, another one is that you can take composition. You can take composition of homotopy groups, like you have with homotopy classes. So if you have a homotopy group of a sphere, you get a homotopy class of Sk to Sl, you can compose it to some space. So that gives you a function from pi L of x to pi k of x. Okay? And something which doesn't exactly come from here, I mean, yeah, it comes from here by a universal example. This operation is called a Whitehead product. This was defined by Whitehead. So it is defined using this. So remember, the sphere, you can think of it as a CW complex with just two cells. So if you have Sk, there is a 0 cell and a K cell, and the boundary is all attached to the 0 cells. That is a copy of the K sphere. Now you can take the product CW complex on Sn cross Sm. So the n plus m minus 1 skeleton of that is just going to be the wedge, the union of these two spaces at a S point, and then there is a n plus m cell. Now the attaching map of this n plus m cell is actually a map from the boundary of this cell, which is Sn plus m minus 1, to this wedge. So this is denoted by this bracket iota n, comma iota m. Iota n for the identity map from Sn to Sn, iota m for the identity map from Sm to Sm. This bracket gives you a homotopy class in pi n plus m minus 1 Sn wedge Sm. This is called the Whitehead product. Okay, this is the Whitehead product. Now for general X, what you will do is you will look at alpha in pi k of x, beta in pi l of x, and then what is going to be this Whitehead product of alpha and beta? It is just going to be, you see, alpha and beta gives you a map from sk with sl to x. So you just pre-compose that with that bracket iota k comma iota l. You pre-compose that, you get an element in pi k plus l minus 1 of x. Okay. Now the property of this is that this bracket, we have suggestively written it using the Lie bracket symbol, because this bracket satisfies the identities of a graded Lie algebra. Okay. So there is so Lie algebra, remember, has two types of identities. One is the skew symmetry, other is the Jacobi identity. So there are for the graded Lie algebra, there are variants of that. This bracket satisfies the identities of a graded Lie algebra. Now in the algebraic model of de Quillen for rational homotopy theory, which takes you to the differential graded Lie algebras, the Whitehead product here, which I have talked about, the Whitehead product on homotopy groups, they provide the underlying Lie algebra structure. So that's where the Lie algebra part comes in, right? Okay. Now let me talk about another important result here about the homotopy category of spaces. This is due to Sullivan. It's called the arithmetic square, saying that simply connected spaces may be studied at one prime at a time, and also there is something about how various primes fit in together. But the fundamental idea is that, in algebra, if you have, say, if you want to look at modules over a ring, what you can do is, so if you have a PID, you can try to localize it at various primes and study the localized modules, and from there you get an idea of the original module. So the thing with topology is that the construction of P localization in algebra, P is a prime, there is an entirely analogous phenomenon in topology, which is also called P localization. There is a P localization functor. Okay? P localization functor, which takes a space X to this X localized at P. So the property of X localized at P is that the homotopy groups of X localized at P are all modules over Z localized at P, for that ring. It's all modules over that. Homotopy groups are all Z localized at P modules. So what will happen is there will be no torsion other than P torsion, and the modules are going to be the free part is going to be something like Z localized at P or something, or extensions of Z localized at P. Okay? And so there is a map, this is called the P localization construction, which starts with a space X and gives you something like, I write X localized at P, whose homotopy groups are all Z localized at P modules. And this map is actually a isomorphism on homology with coefficients in Z localized. It's an isomorphism on homology with Z localized at P coefficients. So this is called a P localization functor. There is also an analogous one for the rationals called the rationalization functor, which takes x to xq. Xq has the property that homotopy groups are all q vector spaces, and this map x to xq is an isomorphism with homology with rational coefficient. All right, and then Sullivan showed that there is an arithmetic square, which he called this an arithmetic square. It says that if x is simply connected, that means the fundamental group is 0 and x is path connected, then there is a homotopy pullback this type. X goes to this is the rationalization, and this is a product of all the p localizations over all the primes. Then you take the rationalization of that product, then that gives you a square, and x is actually a homotopy pullback. So what does that mean? That means that if I know all the p localization, x localized at p's, I know all the rationalization xq, and then I know how the p localizations match with this rationalization. That's what's going to happening in the right bottom corner. Then I will know what is happening with this A. Okay. Then basically it means that if I want to do do some homotopy theory, like you want to study something about homotopy class of maps, you can do it one prime at a time. That's what it says. Okay. So this shows how results in algebra actually have some analog. Sometimes results in algebra they have a direct analog in this homotopy category of spaces. Let's go ahead. Now the next thing is I want to talk about some homotopy classes of maps. So I'm going to talk about homotopy groups, right? It's the main point of this lecture. And so homotopy groups, I have to tell you a little bit about what kind of things you expect in homotopy groups. So you know that there is some homotopy group is pi 1 of S1, which is Z, generated by the identity map, or pi n of Sn is Z, that is also generated by the identity map from Sn to Sn. So that you know, but other than that, you probably are not, you don't know that much about the homotopy groups of spheres. So this is the first example of maps which are outside that the scope of outside the identity maps from between spheres. This Hoff map is the first homotopy class which was there. So this was actually constructed by Hoff. So what he did was, suppose you have a sphere with a multiplication, okay? S1 is a group, unit complex numbers. S3 is unit quaternions. It's a group. So suppose you have a multiplication mu from Sn minus 1 to Sn minus 1, which makes it a almost like up to homotopy, it becomes a monoid. So with identity. Then what you can do is this. There is this Hoff construction. So you take the join of Sn minus 1 with itself. So the join is take join of two spaces x and y is you take x cross y cross the interval 0, 1, and at 0 you identify the various points of y, and at 1 you identify the various points of x. So you can parameterize elements in the join as x comma y comma t. So if you take the join of x and y, it actually becomes homotopic to the suspension of the smash product. So if you take the smash product of Sn minus 1 and Sn minus 1, that gives you S2n minus 2, and the suspension gives you S2n minus 1. The suspension of Sn minus 1 is Sn. So the Hopf construction has a explicit formula like this. So if you have a multiplication, then you can do the Hopf construction, which takes x comma y comma t to mu of xy comma t. It's called the Hopf construction. Okay. So the Hopf construction, I know some examples when this is a group. Namely, I can take S naught. The S naught is plus minus 1. So plus minus 1 is a group because it's isomorphic to the group of order 2. So if I do this Hopf construction, what I get is a map from S1 to S1, and the map has degree 2. Degree 2 map from S1 to S1. Now if I use the group structure on S1, what I get is a map which is denoted by eta from S3 to S2. So what Hopf showed is that this S3 to S2, this is the attaching map for the complex projective plane. And this Hopf map from S3 to S2 actually is a part of a principal S1 bundle, and S2 is CP1 by taking the quotient of S3 with S1. So S1 acts on S3, quotient is S2. So this is the eta, and it also becomes the attaching map for the force cell in CP2. And so Hopf actually realized this map eta is not homotopic to the null map, and actually this gives you this eta becomes a generator of pi 3 of S2, which is isomorphic to Z. This is something Hopf realized, and so although, say, if you are doing homology, you know that the homology of a sphere is very easily computed. Other than if I take reduced homology for hk tilde of Sn, it is 0 unless k is equal to n, where it is Z. So the homotopy groups for k less than n is 0, k equal to n is Z, but this one is the first example where if k bigger than n, it is something non-trivial. It is this Hopf map, I3 of S2 isomorphic to Z. Then if I start with S3 cross S3 to S3, that's the S3 is the unit quaternions, is this multiplication. That gives me an element nu from S7 to S4. This is also homotopically non-trivial. Pi 7 of S4, remember, pi 7 of S4, pi 4n minus 1 of S2n has a copy of Z. This nu will serve as a generator of that. S7 has a multiplication. It is not associative. It is not a part of any group structure, but it has a multiplication which makes it a monoid with identity. Not associative, non-associative monoid with identity. It's called Cayley octanions. Similar to the way you do quaternions, you adjoin one element, you get something, but it cannot be associated. So starting from that, if you do this construction, you get an element sigma from S15 to S8. Again, pi 15 of S8 has a copy of Z. Sigma can serve as a generator. So this Hopf construction is very promising, right? It is starting with multiplications on spheres, you can get homotopy classes of maps. However, there's a theorem of Adams says that after sigma, there is no more of these constructions. So this is where it stops. There is no further of multiplication structures on Sn minus 1, and hence no further these Hopf maps. So there are just So degree 2 map is anyway well known. Other than that, is these three new classes, eta, nu, and sigma. Okay. So let me tell you another thing here. So I said that this computation is very difficult. There aren't many systematic methods of computation for unstable. Unstable is the word stable comes here. You have this suspension functor, and you can take this pi k plus n of sigma nx. You take the direct limit of that. So if you have a f from sk plus n to sigma nx, you can take the suspension of m that gives you an element of pi k plus n plus 1 sigma n plus 1x. You take the direct limit with respect to that. This is called the stable homotopy groups of the space. This process is called stabilization. The stable homotopy groups, there is a lot more systematic techniques and a lot more idea which we have about these stable homotopy groups. And the computation is slightly easier than, although it is still, it's still a big thing, as almost a significant part, all except a finite area is not known. But to tell you what is known, say for unstable homotopy groups, outside this thing, so there is something called a stable range. So if you have X is some K connected, then the stable homotopy groups of X and A homotopy groups matches up to roughly 2K. So that is called the stable range. But outside that is called the unstable homotopy groups. And what is known there is that only up to degree 30 or so is known, and the computations are very difficult. On the other hand, for stable homotopy groups, you can study it one prime at a time again, and even for the prime 2, it is known up to 90, and for other primes, it is known for up to a slightly bigger degree, because the homotopy groups occur at, there are large gaps which gets larger with the prime. So there is some more systematic idea here. Okay, but I don't want to describe all the computations that is known. Let me just tell you something about the techniques and what are the kind of results which I want to talk about today. So one problem here is, if you have a particular candidate, okay, in this homotopy group, so you have a map from Sk to X. How do you show that it is actually non-trivial? So one way of showing that is to show that they induce non-zero maps in cohomology. So for example, you have this Hoff degree theorem, phi n of Sn are isomorphic to Z. So a homotopy class f from Sn to Sn, the degree of f. This comes from the map which is induced by f on homology, right? So the degree of f is that gives the isomorphism. Okay, so that is one method. But you see, if I have a map from Sk plus n of Sn to pi n plus k of Sn, if I have an element there, then this degree will always be 0 if k is bigger than 0, because it's a larger sphere and the homology are in different dimensions. Okay. So the second method to detect non-trivial elements is cohomology operations. So let me just tell you a little bit about how they will detect an element. So suppose you have a map from Sn to Sm such that f upper star h star Sm to h star Sn is 0. So this means that this f is 0 on cohomology. So possibly this is 0 in homotopy also. But I want to say these cohomology operations give you a method to show that it is non-trivial in some cases. So if I take the mapping cone of F, mapping cone of F has cohomology in 2 degrees. One is n+1 and one is m. This is just elementary algebraic topology. Tells you that this is cohomology in 2 degrees, n+1 and m. Now, if there is a cohomology operation from degree m to degree n+1 such that on this mapping cone this cohomology operation is non-zero, then F is not null homotopic. F is not homotopic to star. Why? Because if it was homotopic to star, the mapping cone would become a wedge of Sm and Sn+1, and then this theta would be 0. Okay? Now there is a bunch of cohomology operations which are known. One very big example is the steam rod operations in Z mod 2 cohomology and in Z mod P cohomology. And the steam rod operations actually may be used to show that those classes, eta, nu, and sigma, which I have defined, those are non-trivial. So here I have listed them. This degree 2 map, anyway, it is detected by cohomology, but it is also detected by the operation SQ1. Eta, nu, and sigma are not detected by the cohomology, but it is detected by SQ2, SQ4, and SQ8, respectively. Okay. Yep. So this eta, nu, and sigma we have just defined. These are the Hopf maps. And they are detected by cohomology operations like this. All right. Now, so that's about cohomology operations. They are used to detect these homotopy classes quite often. Now there are something called higher order homotopy operations, which I will just define, give an example that is. And these higher order homotopy operations are used to generate new homotopy classes of maps. One of the examples is what is called a Toda bracket. Now this is, you have to be a bit careful. So what is happening here is you have a sequence of spaces and maps like this, x to y to z to w, and you have two homotopies. This G circle F, that means from x to z, that is homotopic to the constant map, and H circle G from y to w, that is also homotopic to a constant map. So this is called a null homotopy of G circle F. So what you can do, this is called, so using this you can define a new homotopy class called the Toda bracket. What you can do here is this. You look at X, you see G circle F is homotopic to star, and the homotopy you can actually write it as a map from the cone of X to Z. Okay, so you can write the homotopy like this. So you take X inside cone of X, you apply the homotopy that goes to Z, and then you apply this H, it goes to W. Similarly, you can put X inside the other homotopy, H circle G is homotopic to star, that gives you a map from cone of Y to W, and you put X inside the cone of X and you apply the cone of this map F, CF. That gives you map from CX to CY. Okay, and this diagram, these two ways are equal because they are all equal to the map H circle G circle F. Okay, so this gives you a strictly commutative diagram. Okay, but now you see, if you look at the union of two copies of the cone of X, whose intersection is X, if you take the union, that gives you a copy of the suspension of X. So this means that the map will factor through the suspension of x to w. You get this red arrow. Okay, so this red arrow is called the Toda bracket. This red arrow here, this is called the Toda bracket of f, g, and h. It is denoted by this angle f, g, and h. Right? This is called the Toda bracket of f, g, and h. So you remember this is the Toda situation, and this is the Toda bracket. Now let me just point out an example. So this is the first stable homotopy groups of S naught, and it turns out to be Z mod 2 generated by eta. So this means what? This means pi 1 S naught is Sn is actually pi n plus 1 of Sn for n at least 3. It becomes for n at least 3. This value is attained. So that means if I because this is Z mod 2, you see, this means that 2 eta is equal to 0. So 2 eta I can rewrite as 2 composed eta. So 2 means a map of degree 2. This 2 here, this can mean eta plus eta equal to 0, but it also means I can apply a map of degree 2 and then compose with eta that is 0. So I write this 2 eta equal to 2 eta as a composite Sn plus 1 to Sn plus 1 multiplication degree 2 map, followed by this eta is actually a suspension of the Hopf map. Eta, the original eta was from S3 to S2. This is a suitable suspension which gives you a map from Sn plus 1 to Sn. Okay, so it's a composite like this. Now I will go to this Toda situation. Here you see you have 4 things. You have 3 maps, and the consecutive ones are homotopic to star. So you have this Toda situation. To get this Toda situation, you take another degree 2 map on the right. So you have a Toda bracket situation. Sn plus 1 to Sn plus 1 to Sn to Sn 2 eta 2. So 2 times eta equal to 0. Eta times 2 is also equal to 0. So you have this situation. So this is a Toda situation. So that means you can form this Toda bracket. And it turns out that the Toda bracket, this 2 comma eta comma 2, is actually equal to eta square. See, eta square is the composite like this. Sn plus 2, you apply eta to Sn plus 1, and then you apply eta to Sn. So this Toda bracket gives you a map from Sn plus 2 to Sn, and that map is homotopic to this eta square, where eta square is this composite. So the Toda bracket actually gives interesting results, interesting relations in the homotopy groups of spheres. So that is the thing. But it also gives you interesting homotopy classes. This is the theorem. So there are also higher length versions of these Toda brackets. Higher length means that you have a longer, so this one is length 3. You can have length n for any n, but there is a condition under which is defined. It gets more and more complicated depending on n. But there are higher length versions of these Toda brackets. Now this is the theorem. This is proved by Joel Cohen in the 1960s. Says that the stable homotopy groups of spheres are generated from the Hopf maps and their odd primary analogs. There is an odd primary analog of the Hopf map, namely it's called the map alpha. So it is generated by the Hopf map and the odd primary analogs using Toda brackets. Okay. Also, the spaces appearing in the operation. So you see, the Toda bracket is defined with respect to x, y, z, w. So to get homotopy groups of spheres, you should have the first one and the last one should all be spheres. But This also says that the middle spaces in the operations, the middle ones, are actually wedges of spheres. Okay? The middle spaces are all wedges of spheres, so it's actually like a matrix of maps between spheres. So if you take two wedges of spheres, the maps are just given by a matrix of maps between spheres. That's the theorem of Joel-Cohen. This is the Cohen in the, you see, the important thing here is the stable homotopy groups. Now the unstable homotopy groups, what happens is the Toda brackets are not sufficient to prove an analog of Joel-Cohen's theorem. So you need something more, and that's what we were concerned about. We used simplicial shaped operations, and why it is necessary, let me just give an example to point out. So suppose you have this situation, okay? x1, x2, this is an example of simplicial shaped operation, x1, x2, x3, x4. So you have d0 and d1, and you have two homotopies. Epsilon d0 is homotopic to epsilon d1. d0f is homotopic to d1f. So two homotopies you have. If you were in the stable thing, what you would have done is you would have taken d1 minus d0, and then you would have been in the Toda situation. But in the unstable category, you cannot take the difference, so you are not in the Toda situation. So if you have this, then also you can construct an operation like this. You look at the two homotopies. You know these two homotopies, they give you a map from x1 cross 0, 1 to x4. But the maps at the two ends are the same. So you can join the two homotopies together and you get a map from suspension of x1 to x. Okay? So this is an example of a simplicial shaped operation, which is not exactly a Toda bracket. So there are, higher dimensional analog of these operations as well. Okay? And so this is the theorem which we showed. It showed that all the elements of pi k of Sn are generated under simplicial shaped operations by the identity map, Sn to Sn identity, Whitehead products, as I said before, Hoff maps, eta, nu, sigma, their suspension, and their odd primary analogs. Again, the intermediate spaces appearing in the decomposition are all wedges of spheres. Okay? And then there is one more refinement of the theorem. If you allow the suspension operation, so suspension, you get a operation from pi k x to pi k plus 1 suspension of x. We allow that suspension operation. So then you see the suspension of a sk is sk plus 1. So you can consider all the spheres together. And then we have a more general result, which says that all homotopy groups of spheres are generated under simplicial shaped operations and suspensions by the identity map and the Whitehead product. So somehow, strangely, the Hoff map and all, they can be also, like in the suspension thing, we can apply some operation to relate them to these actually the fundamental guys. Okay. Thank you, and that's where I will stop.
Maybe I can suggest please unmute, and thanks Shomik for explaining many beautiful concepts from lovely area of algebraic topology. Ramesh, okay, that's good. Okay, in the chat box, till now I didn't receive any question, but maybe I will ask one question. Can you hear me, Shomik?
Yes,
So,
I can hear you.
if we take a path connected space X, Is it true that there exists some suspension like sigma n or some n, so that sigma n x is homotopic to wedges of sphere? Is it true?
Pick to wedges of spheres.
Uh, like if we take, for example, a CW complex.
No. That
Not
will
true,
not
is
be
it?
true. That is not true. See, you have to have the homotopy type of the stable homotopy type has to be like a wedge of spheres. See, if you take complex
Oh,
projective space, right?
yes. That was the
CP2,
question in my mind. Okay,
CP2,
CP2. Huh.
and the suspension, there is that it's a suspension of the Hoff map is always not null homotopic. So it can never be a wedge of two spheres.
Okay. Okay.
But
That's
I
good.
mean, the thing is, if stably something becomes a wedge of spheres, then there is a large suspension, so that even as a space it becomes a wedge of spheres. That is true.
Then,
So the condition which you are missing over there is that in the stable category it should be the wedge. That condition has to be there.
so can we think about a stable homotopy group of CPN or in particular CP2 also? Is it computable or?
No, stable homotopy group of CP2, it's like, you have
Sphere after some
I
time.
mean, in terms of the sphere, it is computable because there is a co-fiber sequence from S3 to S2 to CP2.
Yes,
And there, you have a long exact sequence. See, the stable homotopy groups, they give you a homology theory. So if
yes.
you have a
Okay.
co-fiber
So
sequence, that gives you a long exact sequence. But the
Thank you for
stable
Samik
homotopy groups of spheres is not computable.
and
So it's very hard.
Sauman for chair the session.
oh, we have one question.
And so
Thomas. Can we
I
take
would
1
like
minute?
I would like to inform all the participants for the paper presenter. Please wait for some technical problem. Please wait
Okay.
10 minutes more. You will get a new link. Then you check your email and then you try to log in from your new link. Please wait 10 minutes more and check it your email.
Thomas.
Yes.
Can we have 2 minutes for this? Because somebody asked question, but I didn't understand.
Okay.
So
Sorry.
he is asking, if we know x away from 2 and x underscore 2, I think that prime 2, localized at 2. So x localized at 2, then can we conclude about x as in arithmetic square?
X localized at 2. Yeah, there is some refinement like that, but exactly, I mean, if you know X away from 2, I mean, if you have to know what, there is some localization where you invert the 2. I guess that's what you would mean by knowing away from 2. So I guess there will be something analogous to the arithmetic square. You
Okay,
can,
so
there is a book by called More Concise Algebraic Topology by Peter May
Peter May.
and others. So there they have this exact relation. What is the most general form of this arithmetic square? And I think if you look at that, this question may be answered there. But
thank you.
the
I
thing
think
is, you have to invert 2. There is that construction you have to do, and you have to take the 2 localization, and then you have to take the 2 inversion of the 2 localization, and then I think still it will be a homotopy pool.
Okay, thank you, Shumik. So it was a
Thank you
nice,
for the
nice talk.
invitation.
Thank you. Good to see you again somehow. So we are connected by something.
Okay.
Okay, have a nice day. Ramesh, shall I don't know where is Ramesh.
Close the meeting, right? It's okay.
But I think Ramesh can control it.
Yes, yes. Thank you, Soman.
Thank you, Ramesh.
Yes,
It
yes,
is good.
yes, yes, yes.
Good. At least we can hear some talks.
Uh-huh.
But I miss Krishnendra's talk because I had to teach that time.
What, Soman?
So Krishnendra's talk. Okay. I had classes. So the same link will work for the
No, no,
parallel
no, no,
session?
no,
Or?
no, no, no. So
Okay.
participants, so there is a technical problem for WebEx. In the same time, is not running a parallel session. So we have created a new link and
Different
we will
link.
be sending to your email ID for new link. Please follow that new link and then you just present your paper. Please check your email. Keep on checking your email. Within 5 minutes, you will get a link and then join. And please wait 5 minutes, 10 minutes, okay? And then join.
But they can wait here, right? If they want to talk among themselves.
Yes, yes, they can wait here to talk, or if you want, they can also leave. But please wait, participants, 10 minutes for getting new link. Just a small part.
One person is remaining. We'll finish in 5.
So one parallel session is going on. So just 5 minutes wait, sir. Okay, sir. Okay. Sir, we will start.
Okay, Dr. Ramesh, we will start.
Okay, sir. Okay.
Yeah, good. Yeah.
Thank you for all the participants attended the National Symposium as well as paper presentation session. I would like to thank for all the participants first and the presenter also. And another, just want to make it update about our National Symposium, how it happened and what are the update. So the update is, first I apologize for the technical inconvenience during the paper presentation session. And thank you for turning up in such a huge number of this number for the symposium. It's pleasure to announce that we had a total registration initially 1,300. In fact, it's a national and international also. So Algeria, and there are many candidate submitted abstract and presented in fact. And we had received abstract for totally 137, and out of that we have selected 74 and shortlisted, and then 15 parallel session conducted, and each parallel session and at least few attendee have attended the paper presentation session, so that we are very happy for that. So in these situations, we had a total number of students attended the symposiums is 341 responses we got, and here is a 79.5% attendee, and 20.5% is present. And then here I want to share with feedback for all those attendee feedback. Here I just want to make it. So these are the feedback for 346 responses we got for as a feedback, and these are the feedback for attendees. And so that so the department IIT Madras is very happy for conducted such events for outside students, for college level and university level students, for giving chance to interact with the faculty, IIT Madras faculty. So with this end note, I request the head of our department, Professor Vetrivel, to give the vote of thanks.
Thank you very much, Dr. Ramesh, for the enormous effort you have put in even in the minute things to see that the program went very well. So I'm sure the topics, all the other people, the participants found it very useful and very interesting. So it's my duty to thank all the people involved in this event. So first of all, I thank our director, IIT Madras, Professor Bhaskar Ramamurthy, for giving his consent and for inaugurating our annual event, NSMA 2021. And also I thank the speakers, amazing talks, very crisp, and so yeah, all the people who all the beginners are able to understand. So such amazing talks, I found it very useful. First of all, I thank Professor Saiju. He had a very busy schedule. He was about to leave for his hometown. Somehow I requested him to give the talk, and I thank Professor Saiju of our department. And next I thank Dr. Krishnedu Kangopatyay, Aiser Mohali, very brilliant talk, and Professor Atul Dixit of IIT Gandhinagar, beautiful talk in analytic number theory. And finally, this afternoon talk, Dr. Samik Basu of ISI Kolkata, related to algebraic topology. So I thank all the chairpersons of the sessions who were throughout the program, and also the student members who were with the secretary throughout the arrangements. So without them, it's very tough. I know that. My wholehearted thanks to Dr. Ramesh Kanchalingam for his immense effort, even in small things, in making this event more fruitful and very effective. I record my sincere thanks to all our colleagues who supported this event, and also the office staff. Also, I take this opportunity to thank, since the number is more, so Ramesh got the idea of streaming the whole event through YouTube. So I thank Mr. Kannan Krishnamurthy of Center for Continuing Education Cell for the live streaming. Also, I record my thanks, last but not the least, on behalf of our department. On behalf of our department, I thank all the participants and all those who presented their papers very sincerely. That's the report I got, Dr. Ramesh. So everything went on well. Ramesh, you want to say any particular participant and want to say something? And you told me that you will be sending the e-certificate for all the participants and also the certificate for the paper presentation by post, right?
Yes. For presenter, we will try to send hard copy.
Okay. For paper.
Yeah, for presenter. Yeah, participants is a very difficulty. The number of people are more, so e-certificate will be provided.
So it's a totally this program was very successful, very grand, and I would say I should again and again thank Dr. Ramesh Kanchalingam for his effort, he and his team, and I hope next year we will have online offline program, same event, and those two participants who have never come to IIT Madras, you can always visit and interact with the people here. And I thank all of you once again for joining this event and staying here throughout. Bye-bye. Thanks, Ramesh.
Thank you, sir. Thank you very much, sir. Thank you very much. The participants, and please, those attendees need a e-certificate. Please fill that form, Google form, the one we shared in the chat box. So presenter list already we have, so therefore directly we will send for presenter certificate. But only I'm just here making announcement that the participant, the attendees, please fill the form so that you may get a e-certificate. If you are not filling, then it's very difficult to reach you. Please make sure your name is be there. Thank you very much. And so we will meet in some another occasions. Thank you very much. Thank you for all.
Bye-bye. Yeah.
Bye-bye. Thank you.